What happens when you crush a star so hard that atoms collapse, protons and electrons merge, and matter itself is squeezed to densities beyond anything on Earth? You get a neutron star, an object so extreme that a single teaspoon of its material weighs more than a mountain. But here's the catch. Even with all our telescopes, satellites, and supercomputers, no one knows what's really at its center. Some say it's a soup of quarks. Others suggest exotic particles we've never seen, and a few believe it hides entirely new laws of physics. The truth is stranger than science fiction. And it's the reason neutron stars remain the most baffling objects in the universe. The crust beneath the surface. Most people think of the heart of a neutron star as the first thing that comes to mind. This is the strange core where physics may not work anymore. But the star's surface and upper shell are already hard to understand, even before we get to the depths. Our Earth's surface, which is what we call it, is nothing like the solid ground we know. Even though it's only a few hundred meters thick, it holds more matter than whole worlds. The crust is made mostly of tightly packed nuclei, the same building blocks of atoms here on Earth, but crushed together in ways our world never experiences. On Earth, the nucleus of an atom is tiny compared to the space around it, with electrons buzzing far away. In a neutron star, that empty space is stripped away. The crust squeezes matter so tightly that nuclei are forced shoulder to shoulder, with almost no room between them. To put it another way, if you could hold just a teaspoon of this crust in your hand, it would weigh about as much as Mount Everest. Even this thin outer crust reaches densities beyond anything we normally encounter. On the very outside, it might still resemble normal matter, heavy iron atoms stripped of their electrons, clinging together like a skin. But just a few centimeters deeper, pressures become so extreme that atoms collapse, electrons are crushed into nuclei, and the matter transforms into something far denser. By the time you're just tens of meters into the crust, each atomic nucleus is sitting in a sea of neutrons that have been squeezed free. It's a landscape where everyday chemistry no longer makes sense, replaced by a bizarre physics playground. The way this layer acts when it's stressed is somewhat odd. Neutron stars spin very fast, and every once in a while they go through sudden changes known as star quakes. These happen because the crust is breaking apart, like an eggshell the size of a planet. The tectonic plates on Earth move slowly, but the neutron star's shell can snap rapidly, releasing huge amounts of energy in a matter of milliseconds. Astronomers have found a link between these cracks in the crust and sudden changes in the pulsar's spin rate. This shows that even this thin skin has a huge effect on how the whole star behaves. The crust also acts like a heat shield. Inside, neutron stars are born unimaginably hot, temperatures reaching trillions of degrees just after their creation. But the crust controls how that heat escapes into space. Its density and composition dictate whether heat leaks slowly or whether it escapes in bursts. In some cases, scientists have observed neutron stars cooling faster than expected, and the crust's structure is one of the first suspects. If the outer layers allow neutrinos, ghost-like particles that slip easily through matter, to escape in large numbers, they can bleed the star's heat away much more quickly than models predict. Another noteworthy aspect about the top is how strong it is. Neutron star crusts were once thought to be unstable, like rock that has been pushed together. Simulations, on the other hand, show that the crust may be the greatest thing in the world. Because the star's gravity is so strong, the atoms lock together into a grid structure that is much stronger than steel. Supercomputer tests show that this layer could hold up under 10 billion times the pressure of anything on Earth and still break. Because it is so strong, the star can keep its almost perfect circular shape even though it spins quickly and has strong magnetic fields. The outer crust gradually transitions to the inner crust, where matter becomes even stranger. At this boundary, densities surpass those of atomic nuclei, and new structures emerge, something scientists call nuclear pasta, where matter organizes into shapes resembling spaghetti, lasagna, or gnocchi. But even before reaching this bizarre layer, The crust already challenges our understanding. The most surprising thing about this layer is probably how little of the neutron star it really shows. Even though it's as heavy as a planet, it's only a thin shell around something 20 kilometers across. The mysterious core is deeper inside the star and holds most of the star's mass. Neutron stars look and act the way they do because of their crust. The shell is what makes everything possible. It holds magnetic fields in place, shapes light pulses, and protects whatever strange matter is below. The nuclear pasta problem. There is a place deep inside a neutron star where matter organizes itself in ways that no one could have imagined. This strange area is known as the nuclear pasta layer because the matter in it doesn't act like regular atomic nuclei. Instead, it bends and squeezes into strange shapes that look like spaghetti strands, lasagna sheets, and even gnocchi-like blobs because of the unbelievably high pressures at the crust core border. The reason for this weird behavior comes down to a tug-of-war between two powerful forces. On one side is the strong nuclear force, which tries to keep protons and neutrons together in compact, dense clumps. On the other side is the relentless pressure and density inside the neutron star, which forces matter to spread out as tightly as possible. Neither side fully wins, and the compromise is that matter organizes into strange, repeating structures, not spherical like normal nuclei, but long rods, flat sheets, or irregular blobs. Scientists first predicted these pasta shapes using advanced computer simulations in the 1980s and 1990s. What surprised them most was how consistently these shapes appeared across different models. At certain densities, long spaghetti strands were the lowest energy solution. At slightly higher densities, the strands would flatten into lasagna sheets. At other points, the structures morphed into gnocchi clumps, or even complex honeycomb-like tunnels. The variety of possible arrangements was so striking that researchers quickly embraced the playful food-inspired names. Nuclear pasta is important for a lot more reasons than just its funny name. This layer might actually be very important in how neutron stars behave. One reason is that it is thought to be very strong, even stronger than the rock. The way pasta is twisted and linked together might make a material tens of billions of times stronger than steel. Neutron stars are very strong, which may help explain why they can keep their shape, even though they spin hundreds of times per second. Another consequence of nuclear pasta is its impact on heat flow. The intricate structures can block or scatter particles trying to move through the crust. This means pasta layers may act like insulation, slowing down how quickly heat escapes from the star's interior. If that's true, neutron stars with thicker pasta layers might cool more slowly than those without. Observations of certain stars seem to back this up, as some neutron stars remain hot for longer than expected, possibly thanks to pasta bottling up their heat. The pasta may also interact with the star's magnetic field. Neutron stars are famous for their colossal magnetic fields, some trillions of times stronger than Earth's. But the way those fields thread through the star depends partly on how the crust conducts electricity. Nuclear pasta, with its strange shapes, may act differently from normal matter. It might trap magnetic field lines, causing them to bend or tangle, which could influence bursts, glitches, or even the long-term stability of magnetars, the most magnetic neutron stars. The link between nuclear pasta and star quakes is one of the most fascinating details about it. Scientists think that when pulsars speed up all of a sudden, it's because the rock broke under the stress. There may be far weird ways for the crust to snap than just a simple break if it has pasta in it. When put under pressure, pasta's strange structures could change shape, stretch, or shift, sending energy out in short bursts that shook the star. These bursts could even explain why magnetars sometimes see strange X-ray flares. What's really amazing is that nuclear pasta might be the most complicated thing in the world. At the atomic level, things on Earth like metals, plastics, and gemstones have designs that repeat. But inside neutron stars, pasta structures are much bigger. They are made up of thousands or millions of particles grouped in complex three-dimensional designs. Some scientists even say that pasta is so complicated that its organization is similar to that of biological structures like proteins. This makes pasta a kind of material cousin to life itself, even though it was born in a very different way. Whilst people have thought about nuclear pasta for decades, no one has ever seen it for real. We can't pick it up or make Earth the same as it is there. Particle accelerator tests are the closest we can get. They smash heavy ions together quickly, achieving densities that are similar to those in the crusts of neutron stars for a short time. These tests give hints that structures that look like pasta might exist, but they don't prove it. Many experts are still sure that nuclear pasta is real, but not because they've seen it. They're sure of it because so many different lines of thinking point to it being true. The superfluid mystery. Most of the time, people think of fluids as rivers of water or air currents moving through the sky. Friction is something that all of these fluids have in common. They stop movement, make commotion, and slow down whatever is going through them in the end. Scientists think that inside a neutron star, there is a type of matter called a superfluid that behaves in a way that no fluid on Earth does. For all time, this kind of quantum matter can move without losing energy, rubbing against itself, or being stopped. It's one of the stranger theories about the inside of neutron stars, and it's also one of the hardest to fully understand. The concept of a superfluid isn't entirely new. Physicists first studied it in laboratories on Earth in the 20th century using helium. When cooled close to absolute zero, helium atoms can suddenly shift into a superfluid state. In that state, helium can creep up the walls of a container, spin endlessly without slowing down, and even pass through tiny cracks with no resistance. What makes this even stranger is that this behavior comes from the collective rules of quantum mechanics, not from individual atoms. Think of something like that inside a star that is heavier than our Sun, and has a density trillions of times higher than anything on Earth. Scientists think that's what neutrons do deep inside a neutron star. When the neutrons are pressed together so closely, their quantum features take over. They don't act like separate particles. Instead, they cooperate to make a single quantum state. In this state, they behave like a single large stream that moves without any resistance. Why do scientists think this superfluid actually exists inside neutron stars? One of the biggest clues comes from the behavior of pulsars. Pulsars are neutron stars that spin rapidly, flashing beams of radiation like a cosmic lighthouse. Most pulsars gradually slow down over time as they lose energy, but every so often, some pulsars suddenly speed up in a strange event called a glitch. These glitches are thought to come from the superfluid deep inside the star. Here's how it might work. The crust of the star spins down as it loses energy, but the superfluid beneath doesn't slow in the same way. Instead, it keeps its original spin speed because there's no friction to drain it. Eventually, the difference between the crust's slower spin and the superfluid's faster spin becomes too large. At some point, the superfluid suddenly transfers some of its angular momentum to the crust, causing the star's overall spin rate to jump forward. Astronomers detect these sudden jumps as glitches, and they happen too often and too consistently to be explained by any other process. The way neutron stars cool down is another sign about superfluidity. Neutron stars are cooling faster than models say they should, according to observations of some of them. The fastest explanation for this cooling is the presence of superfluid neutrons, which make it easier for neutrinos, which are very light particles that look like ghosts, to leave. Neutrinos take heat away, and when superfluidity sets in, they stream out faster, lowering the temperature of the star. These rates of cooling don't make sense without superfluid physics. Superfluid matter inside a neutron star isn't just strange, it's also incredibly powerful. On Earth, superfluids are delicate, requiring careful experiments at ultra-cold temperatures to create them. But in a neutron star, superfluidity doesn't mean fragility. The superfluid here is squeezed by gravity billions of times stronger than anything we know, and yet it flows with perfect efficiency. Some calculations suggest that if you could scoop out even a teaspoon of this star superfluid, It would weigh as much as a mountain. And yet it could spin endlessly in a container without ever slowing down. The way this state stores cycle is one of the weirdest things about it. When we spin water in a bucket on Earth, it stops spinning after a while. But superfluids can't lose their angular momentum slowly over time. Instead, they store their spin in tiny whirlpools that look like tornadoes and are punctuated by thin vortices. There could be billions of these swirls inside a neutron star's superfluid, all lined up with the star's spin. Since the star is moving more slowly over time, the swirls change by snapping, changing, or moving outward. The pulsar glitches we see from Earth are caused by the crust being jolted by each shift. It's like a pinball machine the size of a star, with quantum whirlpools as the bumpers. Additionally, superfluidity and superconductivity may exist at the same time in neutron stars. It is possible for protons in the same setting to become superconducting, while neutrons become superfluid. That means that not only does matter flow freely inside the star, but electrical currents may also move freely. It's possible that this mix is what holds neutron stars' huge magnetic fields in place and controls them. This includes magnetars' scary magnetic fields. If this is true, the insides of neutron stars are both the most extreme superfluids and the greatest superconductors in the world. The problem is, while all these theories match certain observations, no one can directly confirm what's happening inside. We can't drill into a neutron star, and we can't recreate the pressures and densities in any lab on Earth. The best we can do is compare models to what pulsars and magnetars show us, their spin rates, glitches, bursts of energy, and cooling behavior. The superconductor core. When people hear the word superconductor, they often picture future trains that float on magnetic fields or test materials that let electricity flow through them without any problems. Neutron stars, on the other hand, look like toys compared to what's inside them. Scientists think that the protons can form the universe's strongest superconductor, one that not only lets electricity flow easily, but also controls magnetic fields on a cosmic scale, deep inside its core, beyond the already strange superfluid neutrons. To understand why this is so incredible, let's start with what superconductivity means. On Earth, superconductors are special materials that, when cooled to extremely low temperatures, allow electrical current to flow with zero resistance. That means no energy is lost to heat, unlike in normal wires. But superconductors here are fragile. They require careful cooling and only work under very specific conditions. Inside a neutron star, however, nature may create a superconductor that makes our best materials look primitive by comparison. The recipe begins with protons. Even though neutron stars are mostly made of neutrons, a small fraction of protons and electrons is always present. Normally, protons repel each other because they carry positive charge. But at the crushing densities inside a neutron star, they may overcome that repulsion by pairing up into so-called Cooper pairs. This pairing is the same process that allows superconductivity in metals on Earth. Once paired, protons can glide through the star's interior without electrical resistance. Now add the scale. In a neutron star core, you don't just get a few stray superconducting currents, you get a sea of them stretched across an object that may be 20 kilometers wide and holding more mass than our Sun. This ocean of superconducting protons has the power to trap and shape magnetic fields in ways no human-made superconductor ever could. Superconductivity has a very interesting effect. It explains why neutron stars have such strong magnetic fields. Some neutron stars can have magnetic fields that are 1 trillion times stronger than Earth's. The bigger cousins of these are magnetars, which can reach forces 1,000 times stronger. If we tried to make even a small amount of these fields here on Earth, they would destroy even the most powerful tools. In spite of this, neutron stars not only make them, but also keep them steady for millions of years. The key is superconductivity, which means that superconductors make magnetic fields flow through thin, quantized tubes called fluxoids. The fields cannot move because of these tubes holding them in place. This might also explain why neutron star magnetic fields sometimes rearrange violently, releasing bursts of energy. When fluxoids shift, merge, or snap under pressure, the magnetic field above the star's surface can be rewired in an instant. Observers on Earth see this as sudden intense X-ray or gamma-ray flares, especially from magnetars. Without superconductivity, these events would be hard to explain. The way neutron stars cool is another reason why experts think their cores are superconducting. The proton superconductor changes how heat moves through the star. It speeds up some cooling pathways and slows down others. For example, superconductivity changes how neutrinos are made and released. Neutrinos are those ghostly particles that come out of stars. Astronomers can figure out if superconductivity is important by looking at the cooling curves of neutron stars. The fact that the data often matches models where proton superconductivity exists suggests that it's not just an idea, but a real thing about these stars. Even the crust's glitch events may connect back to the superconducting core. Remember, the neutrons in the interior may form a superfluid that stores angular momentum in quantized vortices. The superconducting protons, on the other hand, pin magnetic fields in place through their flux tubes. When vortices and flux tubes interact, they can lock together or suddenly break apart, transferring energy violently to the star's crust. This coupling between superfluid and superconductor could explain why glitches happen with such suddenness and power. What makes the superconducting core even more fascinating is how alien it would appear if we could observe it directly. On Earth, superconductors are laboratory curiosities, fragile states of matter that collapse under heat or pressure. In a neutron star, the opposite is true. Here, superconductivity is not a delicate exception, it's the natural state. Crushing density and extreme gravity create conditions where protons have no choice but to become superconducting. Instead of being rare, it might be the dominant form of matter over vast regions of the core. There's also the scale of the currents. On Earth, a superconducting loop can carry electricity indefinitely, perhaps a few amps, without ever losing energy. Inside a neutron star, superconducting currents could carry unimaginable flows of charge, sustained across distances of kilometers and kept alive for millions of years. These currents not only shape magnetic fields, but may also stabilize the star against collapse by redistributing energy. Still, the superconducting core, along with everything else inside neutron stars, can't be studied directly. They are too high for Earth, and not even the strongest particle reactors can reach them. Scientists use things like the way magnetic fields behave, how fast stars cool down, and the patterns of pulsar glitches as secondary proof. There is a lot of proof that neutron stars are based on superconductivity, but there isn't a single observation that shows it, for sure. The equation of state dilemma. Scientists who study physics will generally say that the equation of state controls how matter acts. An equation of state is a simple mathematical formula that shows how pressure, temperature, and density are related. The ideal gas rule says that pressure times volume equals temperature times a number. This is true for gases like air. We can use other well-tested models to figure out how hot plasma acts at different depths in stars like the Sun. But when it comes to neutron stars, this equation, called the equation of state, is one of the biggest scientific mysteries the world has yet to answer. Neutron stars are in a place where no known equation works exactly, which is the trouble. Their inside crushes are much more important than anything we can make on Earth. Densities inside can be many times higher than the densities of atoms. That's not just a little more extreme. It's like putting all of humanity into a sugar cube. Things may act in ways we've never thought of at those sizes, and no one theory can explain it all. Physicists have proposed many different equations of state for neutron star matter. Some assume that the interior is made mostly of neutrons with a sprinkling of protons and electrons. Others suggest exotic ingredients like hyperons, kaons, or even free quarks. Each possibility leads to a slightly different equation of state, and each predicts different outcomes for how a neutron star should look, spin, or collapse. The equation of state determines how much pressure exists at a given density. That pressure, in turn, tells us how big a neutron star of a certain mass should be. If the equation of state is stiff, meaning it predicts high pressure, then neutron stars should be relatively large in radius for their mass. If it's soft, with lower pressure, then neutron stars should be smaller and more compact. Observations of neutron stars, their radii, masses, and behaviors, are the only clues we have to figure out which equations match reality. For example, some neutron stars weigh over 2 solar masses but don't collapse into black holes. That tells us the true equation of state must be stiff enough to hold up that weight. But at the same time, other observations suggest neutron stars can be very small, perhaps only 11 kilometers across, which favors a softer equation. Reconciling both sides is like trying to solve a puzzle where the pieces don't quite fit together. The merging of neutron stars is one of the best ways for scientists to test these theories. Gravitational waves are ripples in space-time that are made when two neutron stars crash into each other. The shape of those waves shows how soft or stiff the stars were before they merged. A stronger equation of state makes it harder to bend stars, while a softer one makes it easier for them to do so. Scientists can figure out which equations of state are most likely to be true by looking at the gravity waves from events like GW 170817. In spite of this, there isn't a clear winner yet. An X-ray test is another way to check. When NASA's NICE mission is on the International Space Station, it looks at neutron star surfaces for fires. You can see these points moving across the screen as the star spins. The X-ray light curves show how gravity bends light around the star. Astronomers can figure out both the star's mass and its radius from how it bends. Once more, these numbers should lead to a clear expression of state. The results so far, on the other hand, are painfully mixed. They rule out some extreme models, but leave many others open. The stakes are high because the equation of state isn't just an academic exercise. It's the key to unlocking what matter is truly made of at the smallest scales. If quark matter exists inside neutron stars, the equation of state will look completely different than if it's only neutrons. If hyperons appear, or kaons, or some other exotic particles, the pressure-density relationship will change dramatically. In that sense, neutron stars are like cosmic laboratories, running experiments we can't perform on Earth. By deciphering their equation of state, we learn not just about stars, but about the fundamental building blocks of the universe. The question of maximum mass comes up too. There are different formulae that say how heavy a neutron star can get before it turns into a black hole. Based on some calculations, the maximum seems to be around 2 solar masses. Others accept stars that are up to 3 times the mass of the Sun to be much heavier. Neutron stars on the higher end are very hard for scientists to explain, because if the stars are real, then any equation that can't explain them must be wrong. Big changes in astrophysics are caused by small changes in physics at the quantum level. This is one of the most interesting things about the problem. A small change in how nuclear forces work can make a neutron star look kilometers bigger or smaller than it really is. The expected maximum mass can be doubled or cut in half by making a small change to the way protons and neutrons are thought to interact. Neutron stars are very sensitive, which makes them both one of the best and worst places to test nuclear physics. The sound of matter at 1 trillion degrees. You probably picture something moving through the air when you think of sound, like music from a speaker, rain in the sky, or someone talking across a room. But sound isn't just in the air, it's just a wave or ripple of pressure going through something. How stiff and thick something is affects how fast sound moves through it. On Earth, sound moves most slowly through air, then through things like steel, then through water. But inside a neutron star, the rules of sound are so strange that they don't even seem real. Scientists think that sound waves inside a neutron star may move faster than 30% of the speed of light. This is so fast that even the fastest fighter jet would seem to be standing still. To understand why, let's think about what controls the speed of sound. The key is how quickly atoms or particles in a medium can push back when compressed. Air molecules aren't very stiff, so sound moves at only about 343 meters per second at room temperature. In water, molecules are packed more closely, so sound jumps to around 1,500 meters per second. In steel, where atoms are locked in tight bonds, sound travels about 6,000 meters per second. Now scale that logic up to matter squeezed denser than an atomic nucleus, and you begin to see why neutron stars make sound speeds that are off the charts. Inside a neutron star, matter is crushed to such extreme densities that even neutrons themselves feel packed almost shoulder to shoulder. When you push on this kind of matter, it doesn't just resist a little, it pushes back almost instantly with staggering force. That resistance translates into pressure waves, sound, racing through the core at relativistic speeds. The numbers are almost unbelievable. 1/3 the speed of light is nearly 100,000 kilometers per second. That means a sound wave could cross the entire 20-kilometer diameter of a neutron star in less than 1,000th of a second. This extreme speed of sound isn't just a curious fact, it's also one of the strongest clues to the true nature of matter at such densities. By definition, sound speed tells scientists how stiff matter is at a given density. If sound moves faster, the matter is stiffer. If slower, the matter is softer. And stiffness connects directly to the mysterious equation of state, the mathematical relationship that describes how neutron star matter behaves. Observations of neutron star mergers, pulsar timing, and surface radiation all indirectly tell us how fast sound must be moving inside. So, the speed of sound is one of the most valuable tools scientists have for peering into the unseen heart of these stars. According to Einstein's relativity, nothing can move faster than light. But sound isn't made of particles moving in space. It's a wave traveling through matter. Still, relativity puts limits on how fast sound can get. Theoretical work suggests that if sound speed ever approached the full speed of light, it would cause matter to behave inconsistently with relativity's rules. Yet inside neutron stars, the observed masses and radii suggest that sound speed gets surprisingly close to that cosmic limit, brushing against the edge of what's theoretically possible without breaking physics. In addition to being strange, different parts of the neutron star may be able to carry sound at different speeds. Sound may only move a small part of the speed of light in the upper shell. It goes through the roof at almost 1/3 of the speed of light or faster in the thick inner core. Some models even say there might be quick jumps where matter changes phases, like when water freezes into ice and the speed of sound changes right away. In a neutron star, sound might not move easily. Instead, it might hit walls and bounce back, making echoes inside the star's body. The possibility of these starquakes, sudden shifts in the neutron star's crust and core, may also connect to sound. When stresses build up, the release could send seismic waves ringing through the star. But unlike earthquakes, which rumble across Earth for minutes or hours, these seismic events would ripple through a neutron star in fractions of a second, powered by sound speeds far beyond anything we know. Astronomers suspect that some of the sudden bursts of radiation we see from magnetars may actually be linked to such starquakes, with sound waves shaking the crust and triggering violent energy releases. In addition, the weather adds another twist. Neutron stars that are just starting out are unbelievably hot, up to 1 trillion degrees in their early days. When temperatures are this high, sound doesn't behave the same way it does in normal matter. Quantum impacts are more important. Particles move together in groups, and sound waves are not just simple changes in pressure, but more like coordinated quantum excitations. Sound moving 1/3 of the speed of light at 1 trillion degrees goes against everything we know about sound and makes us think outside of normal physics. What would actually sound like inside such a star? Of course, no human ear could ever hear it, and the environment is so dense and exotic that the term sound is almost metaphorical. But scientists sometimes simulate these waves as oscillations. The tones would be unimaginably high-pitched, far above the range of human hearing. In fact, neutron stars may literally ring like cosmic bells after certain events, sending their sound vibrations outward as gravitational waves. When detectors like LIGO and Virgo pick up these ripples, they are, in a sense, listening to the echo of sound waves moving through matter denser than anything else in the universe. Hyperon invasion. Neutrons are what neutron stars are made of, but what happens when other weird particles show up? It's this puzzle that leads to the so-called Hyperon attack. Hyperons are related to protons and neutrons, but they are larger and less familiar. They have at least one strange quark, which is a type of subatomic particle that isn't usually found in matter. When things are normal on Earth, hyperons break down almost quickly, but hyperons might suddenly become stable deep inside neutron stars, where pressures are crushing and densities are higher than anything we can make in a lab. The possibility of hyperons showing up inside neutron stars is both fascinating and problematic. On one hand, it would mean that neutron stars are like particle accelerators on a cosmic scale, creating forms of matter we can't build on Earth. On the other hand, their very existence throws star models into chaos. This paradox is known as the Hyperon puzzle, one of the thorniest issues in modern astrophysics. The neutrons and protons inside a neutron star are squeezed so tightly that eventually it becomes energetically favorable for some neutrons to transform into hyperons. It's like the star saying, "I can save energy by rearranging my particles this way." The result is that neutrons give way to hyperons, such as the lambda, sigma, or Xi particles. These names come from the particle zoo in high-energy physics, but to a neutron star, they might just be part of daily life in its core. The trouble comes with what hyperons actually do. They don't provide as much pressure support against gravity as neutrons and protons do. That means if hyperons appear in large numbers, the star should become less stable. In fact, many equations of state that include hyperons predict that neutron stars shouldn't be able to hold masses above about 1.5 times the Sun's mass. But astronomers have observed neutron stars with more than twice the Sun's mass. That should be impossible if hyperons are abundant. Yet we have good reasons to think they are. The data says massive neutron stars exist, but theory says hyperons should make them collapse. Both can't be wrong, so something is missing in our understanding. Some researchers suggest that additional forces, like repulsion between hyperons, might stiffen the equation of state and allow stars to stay stable. Others think exotic states of matter, like quark matter, may appear just as hyperons do, balancing out the loss of pressure. Either way, hyperons seem to force us to rewrite the rules of dense matter. The way hyperons might affect cooling is a very interesting part. Neutrinos, those ghost-like particles that zip through matter almost without being noticed, are the main way that neutron stars send out energy. If hyperons are present, they could make it easier for neutrinos to be made in new ways. That would let the star lose energy a lot faster than normal, which would make it cool down very quickly. It does look like some neutron stars cool down faster than predicted, and hyperons are one of the main ideas behind this. Neutron stars could also spin and glitch because of hyperons. Pulsars, which are neutron stars that work like lights in space, spin very quickly. They sometimes speed up all of a sudden, which is called a glitch. Hyperons may be present in the core, and their reactions with superfluid neutrons and superconducting protons may be a cause of these sudden changes. Even though it hasn't been proven, models with hyperons tend to suggest more complex internal processes than models without them. Another clue comes from heavy ion collisions on Earth. In massive particle colliders, like the Large Hadron Collider, scientists smash gold or lead nuclei together at nearly light speed. For a fleeting instant, the resulting plasma reaches densities and energies similar to those inside neutron stars. Hyperons do appear in these collisions, and studying them helps researchers guess how they might behave under stellar conditions. But the experiments last only fractions of a second, while neutron stars endure for billions of years. Translating between the two remains a massive challenge. The existence of hyperons inside neutron stars could even impact gravitational waves. When neutron stars merge, the exact way they squash and wobble depends on their internal makeup. If Hyperons soften the star's equation of state, the gravitational wave signal will look different than if the core is only neutrons. Scientists are already using detectors like LIGO and Virgo to study these ripples, hoping to spot subtle signatures that might betray the presence of Hyperons. It's a cosmic detective story played out through vibrations in space-time. Kaon condensates. Hyperons are like strange cousins sneaking into the core of neutron stars. Kaons, on the other hand, are more like unexpected guests from a different part of the particle family. Kaons are mesons, which are a type of particle. Mesons are made up of only two quarks, one quark and one antiquark. Protons and neutrons are baryons, which means they are made up of three quarks. Kaons are unstable and break down quickly on Earth. They only show up when high-energy particles hit each other. But some scientists think that kaons might do something very strange in the dense interiors of neutron stars. They might compress into a stable state, creating something called a kaon condensate. Think about how water mist turns into liquid when the temperature drops to get an idea of what that means. Gas molecules might not form a pool in this case. Instead, kaons might join together to make a strange quantum liquid deep inside the star's core. It would make a form of matter that is unlike anything we've seen on Earth before. So why would kaons condense at all? It comes down to energy balance. Neutron stars are so dense that normal neutrons and protons can't carry the load forever. At extreme pressures, it may be more efficient, in terms of energy, for the star to replace some of its particles with kaons. Kaons have the ability to help neutralize electric charges in the dense plasma, especially because they can carry negative charge. By condensing, they relieve some of the system's energy burden. The star essentially chooses kaons as the cheapest way to reorganize itself. If kaons condensed, terrible things might occur. Like hyperons, kaons don't put as much pressure on the outside as neutrons and protons do. The equation of state, which is the rule that connects pressure and density, gets weaker if kaons take over a big part of the star's core. In other words, the star would get smaller and weaker. Yes, the star would fall apart into a black hole if it had too many kaons. Astrophysicists call this the Kaon puzzle, because theory says they should show up. But many neutron stars might not last long if they do. We still see a lot of neutron stars that have been around for a long time. Some experts say that Kaon condensates might be able to explain some findings, like the fact that some neutron stars cool down very quickly. Neutrinos are ghost-like particles that are easy to leave and take away heat. Kaons would give the star new ways to make them. Having kaons in neutron stars could make them lose energy faster than models that don't have them show. Look at neutron stars that are cooling, like the one in the constellation Cassiopeia. A supernova debris have shown temperature drops that are faster than predicted, and kaons are still being thought of as a possible cause. Kaon condensates might also leave fingerprints in neutron star mergers. When two neutron stars collide, their interiors mix and churn violently, producing gravitational waves and flashes of light. If kaons are lurking inside, the merged star's behavior could shift. The gravitational wave signal might carry subtle differences, depending on whether kaon condensation had softened the cores. In this way, observatories like LIGO and Virgo may one day confirm or rule out their presence simply by listening to the ripples in space-time. Kaon condensates could set the stage for even stranger states of matter. Once kaons appear, the star's pressure and composition shift in ways that may make it easier for quarks themselves to break free from confinement. That means kaon condensation might be a stepping stone to quark matter, where neutrons and protons dissolve into a soup of fundamental particles. In this sense, kaons are more than exotic intruders. They may be the heralds of a deeper transformation in the star's core. Particle reactors with heavy ions are the best place on Earth to study kaons. When cores of gold or lead are smashed together very quickly, kaons show up in the rain of particles. Scientists want to know how kaons act at very high numbers by studying their features. The trouble is that these tests only last trillionths of a second, while neutron stars stay around for millions or even billions of years. At this point, we are not able to make Kaon condensates again or prove that they exist in a lab. Theorists keep running simulations though, and kaons won't go away from the models. Adding kaon condensates can help explain neutron stars that aren't the usual size or cool down at the normal rate. Sometimes, the predictions don't match up with what has been seen, which forces experts to change their theories. The debate goes on. If kaons are found inside neutron stars, they could change a lot of what we think we know about dense matter. Something just as strange must be there in their place if they don't show up. Quark soup hypothesis. Visualize breaking apart a neutron, which is already one of the densest things you can think of, so badly that the quarks inside it are free to move around. That's the main idea behind the quark soup hypothesis. Neutrons and protons may break down into their quark parts at very high densities inside the cores of neutron stars, forming a new type of matter called quark matter. On Earth, quarks never roam freely. They're always locked inside larger particles, bound together by the strong nuclear force. Physicists call this property confinement. But under crushing pressures, theory suggests that confinement might break down. Instead of behaving like individual neutrons or protons, matter may become a fluid of quarks moving around freely, mixing like ingredients in a soup. The quark soup is no ordinary liquid. It's thought to be one of the most exotic states of matter in the universe, rivaling even black holes in strangeness. In laboratories like the Large Hadron Collider, physicists have briefly created something similar called the quark-gluon plasma, where quarks and gluons, the particles that carry the strong force, roam free. But those experiments last only trillionths of a second and require temperatures hotter than the center of the sun. In neutron stars, instead of extreme heat, it's the insane density that forces quarks to deconfine, possibly creating a permanent quark soup in the star's heart. Many mysteries have been solved for a long time if quark matter exists in neutron stars. For instance, quark matter might be able to explain why some neutron stars are surprisingly small. Matter that is normally full of neutrons can only be pushed so far before it turns into a black hole. Neutrons, on the other hand, can break down into quarks, which weakens matter so that it can be packed into a smaller space without falling apart right away. This would make neutron stars that are very small and dense. These stars, which have a shell of neutron matter and a core of quark soup, are sometimes called hybrid stars. The merging of neutron stars is another possible sign. When two stars crash into each other, the conditions inside them go beyond anything that has ever been seen in the universe. If there is quark matter, the crash could cause a phase change in real time, turning regular matter into quark soup. The gravity wave signal would be changed by that quick change, leaving a unique fingerprint that scientists could find using LIGO and Virgo. In this way, gravity waves could one day show that quark matter exists without us having to touch it. It's one of the weirdest ideas that quark matter might not only exist, but be more steady than regular nuclear matter. If that's true, quark matter might want to stay that way once it forms. Some scientists even say that quark matter could make up whole stars, which are called quark stars. From far away, these would look like neutron stars, but on the inside, they would be very different because they wouldn't have a shell, an outer core, and an inner core. Neutron stars of the same mass might be a bit bigger and heavier than quark stars, and they might cool down in different ways. The quark soup hypothesis also introduces a whole menu of exotic physics. Quarks come in different flavors. Up, down, and strange are the lightest ones. In neutron stars, it's likely that strange quarks would join the mix, creating strange quark matter. This hypothetical form of matter could be so stable that if even a small droplet of it escaped a neutron star, it might convert any normal matter it touched into more strange matter. That's why physicists sometimes call it infectious matter, though thankfully that's only speculation. There are also questions about how quark soup would behave under quantum rules. Would it flow like a perfect liquid without any resistance, the way quark-gluon plasma seems to in colliders? Would it exhibit color superconductivity, where quarks pair up in bizarre patterns, conducting currents unlike anything we see in metals? If so, the inner life of a neutron star might be more like a quantum laboratory than anything resembling a star. Even though the idea is very well thought out, it is very hard to prove quark soup. We can't look right into the heart of a neutron star, and we can't make it happen on Earth for more than a split second. That's why astrophysicists use gravitational waves, X-ray signs, pulsar time, and cooling rates as hints that quark matter might be out there. There isn't a single piece of proof that has solved the case yet. But more and more hints keep coming up, and a lot of scientists think we're almost there. Color superconductivity. Color superconductivity is the idea that the quarks that are freed up from neutrons might organize themselves into one of the weirdest states of matter in the universe. Quark soup is the crazy idea that neutrons break down into their smallest parts. Before we can figure out why, let's go back to the normal world of superconductors on Earth. Cooper pairs are made up of 2 electrons. They can be found in a normal superconductor, which is a certain type of metal that has been cooled almost to absolute zero. They can move through the material without any problems because they are paired together. This means that electric currents can flow forever without losing power. It's one of the most amazing things that can happen in physics. Apply that same idea not to electrons but to quarks, the building blocks of neutrons and protons. Quarks carry a property called color charge, which has nothing to do with visual color, but is the way they interact through the strong nuclear force. Just as electrons can form pairs that make superconductivity possible, quarks may also pair up under the right conditions. The result isn't an ordinary superconductor, it's something theorists call color superconductivity, where the strong force behaves in bizarre new ways. Inside a neutron star's core, where pressures and densities reach unimaginable levels, conditions may be perfect for color superconductivity to arise. Instead of just a random soup of free quarks, they could align and bond in patterns, producing exotic phases of matter that have no counterpart on Earth. This wouldn't be superconductivity for electricity, but rather superconductivity for the strong force itself, a kind of perfect conductor of color charge. There are different possible patterns for how quarks might pair. One proposed phase is the two-flavor superconducting phase, where only up and down quarks, the lightest flavors, form pairs. Another more exotic option is the color-flavor-locked phase, where up, down, and strange quarks all lock together into a highly symmetrical state. In this phase, all quarks are paired, and the symmetry is so complete that it might be the most stable form of matter possible. If color-flavor locking exists, it could mean that the ultimate fate of many neutron stars is to transition into stars made entirely of this exotic stuff, sometimes referred to as strange stars. It's hard to believe what color superconductivity means. For starters, it would change the star's qualities in a big way. If the star's core is made of color superconducting quark matter, it could change how it glitches, how it spins, or even how it makes magnetic fields. As with electrical superconductors, color superconductors push out certain fields. This is known as the Meissner effect, and it can have a big impact on how the magnetism of a neutron star changes over time. With their mind-bogglingly strong magnetic fields, magnetars may have some of their traits due to this strange kind of physics at their heart. Cooling behavior is another area where color superconductivity could matter. Neutron stars radiate energy mainly through neutrinos, those nearly invisible ghost particles that stream freely out into space. If the star's core is a color superconductor, the rate at which neutrinos are produced and escape could be either suppressed or enhanced, depending on the specific phase. This would affect how quickly the star cools over millions of years. Observations of neutron stars with unusual cooling curves are already pushing scientists to ask whether exotic phases, like color superconductivity, might be responsible. There's also a link to gravitational waves. When neutron stars merge, their interiors are squeezed, stirred, and heated in ways we can't replicate anywhere else. If color superconducting matter is inside, the merger's gravitational wave signal could reveal it. The exact way the merged star vibrates, oscillates, or collapses depends strongly on its inner physics. Observatories like LIGO and Virgo may one day pick up these subtle differences, effectively giving us an indirect glimpse of color superconductivity in action. Heavy ion collisions in particle reactors are the only way we can get close to these conditions here on Earth. Quark gluon plasma is made by smashing gold or lead nuclei together almost at the speed of light. It is similar to the quark soup that scientists think is inside stars. But in those tests, high heat is used instead of extreme density. Density is what matters most in a neutron star, which changes all the rules. We still can't do that in the lab, so ideas about color superconductivity aren't proven. However, these theories are based on the same quantum field theory that has been tried many times in particle physics. Some researchers even propose that if color superconductivity is real, it might represent the most stable state of matter in the universe. In this view, everything we see, stars, planets, people, is just ordinary matter perched on a higher energy shelf, while the true lowest energy configuration of quarks is this superconducting state. If a large enough neutron star core transitions into it, the process might spread, potentially converting the entire star into a strange star. That possibility alone makes color superconductivity one of the most compelling and unsettling frontiers in astrophysics. There are signs, but not proof, that color superconductivity could help scientists figure out some problems in the science of neutron stars. Neutron stars that are more than 2 times the mass of our Sun, for example, are hard to explain with normal matter alone because they are stable. Adding quark matter and color superconductivity to the mix could make the star less likely to fall apart. Some models of pulsar glitches and spin irregularities also work better when strange stages like color superconductivity are added. The maximum mass mystery. Neutron stars walk the line in nature. A star that is dense enough to crush atoms is stable on one side and is held up by the pressure of neutrons that stop it from falling apart even more. This side is dangerous. If you tip the scales just a little, the star will fall and turn into a black hole. Because of this sensitive balance, scientists have been wondering for a long time, how much mass can a neutron star have before it falls apart? For decades, the answer seemed straightforward. Based on nuclear physics and the equations describing dense matter, researchers predicted that neutron stars couldn't be heavier than about 2 solar masses. Anything larger should be impossible because the inward pull of gravity would overwhelm all other forces. Yet as telescopes grew sharper, astronomers began to find neutron stars that defied this neat limit. Take PSR J0740 plus 6620, a pulsar discovered in 2019. Careful timing measurements of its radio pulses, combined with the bending of space by its companion star, revealed a mass of about 2.14 times that of the Sun. That number might not sound far above the limit, but in the razor-thin margin between neutron stars and black holes, it's enormous. If PSR J0740 plus 6620 is real, and evidence strongly suggests it is, then either our understanding of matter at extreme densities is incomplete, or neutron stars have hidden support mechanisms we haven't accounted for. It's not the only one. Other big stars, like PSR J0348 plus 0432 and PSR J1614 2230, are also close to or above 2 solar masses. Even more interesting are ideas that stars may have as much as 2.3 or even 2.5 times the mass of the Sun. Each of these new findings breaks up the clear picture we had before and makes the maximum mass even less certain. Why does this matter so much? Because the maximum mass of neutron stars is directly linked to the equation of state, the rulebook that describes how matter behaves at extreme density. If the maximum is too low, then exotic states like hyperons or Kaon condensates must appear early, softening the star and forcing collapse. If the maximum is higher, then something inside the star is providing extra resistance. That something could be quark matter, color superconductivity, or even a form of pressure we haven't yet discovered. When we think about spinning, the puzzle gets deeper. Neutron stars spin very fast, which helps them fight gravity even more. In theory, a neutron star that spins quickly could be heavier than one that spins more slowly before it collapses. In other words, the maximum mass is not a fixed number, but a point that changes with the speed of the star's rotation. Some scientists think that stars like PSR J0740 plus 6620 may only exist because they spin so fast, which keeps them from collapsing for now. They might cross the imaginary line and turn into black holes if they slow down. The maximum mass mystery also connects to the question of whether twin stars exist. These are hypothetical pairs of neutron stars, with the same mass but radically different internal structures, one made of normal nuclear matter, the other hiding a quark core. If such stars exist, then the maximum mass might not be a hard cutoff, but a branching point, where stars of the same size could either hold together or collapse, depending on what's inside. Some astrophysicists have suggested that the maximum mass could provide a natural boundary in the universe. Neutron stars heavier than about 2.5 solar masses would collapse into black holes, while lighter ones remain neutron stars. This divide might explain why black holes observed through gravitational waves almost always start at about 5 solar masses or higher. The gap between 2.5 and 5 solar masses, often called the mass gap, may reflect how nature separates neutron stars from black holes. Yet the discovery of heavier neutron stars could blur or even erase this line entirely. To add to the mystery, the highest mass may change with age. Because of temperature pressure and spin, a newly formed neutron star that is still hot and rough from a supernova might be able to hold more mass for a short time. The same star might not be able to stand up in the long run as it cools down and moves more slowly. To put it another way, a neutron star might be safe and steady at birth, but upon crossing the unseen line millions of years later, it will be doomed. The twin star hypothesis. Think about two stars that are exact copies of each other. They have the same mass, size, and speed of spin. On the inside, though, they are very different. One is made up of neutrons packed together in a dense and recognizable nuclear structure, while the other has an exotic quark core that is made up of basic particles that are unlike anything on Earth. This is the twin star hypothesis. The idea that neutron stars with the same mass could be in very different states of matter based on what's inside them. At first glance, this sounds impossible. After all, if two objects weigh the same and occupy the same space, shouldn't they also be built the same way? In everyday life, yes. Two cars that weigh the same probably have similar amounts of steel, glass, and plastic. But neutron stars don't follow everyday logic. Their structure depends on the equation of state, the rulebook for how matter behaves under extreme density. And the equation of state isn't simple. In fact, it may have multiple stable solutions at the same mass. That's where twin stars come in. A neutron star's outer layers are made of neutrons and a smattering of protons and electrons, all packed together in exotic forms like nuclear pasta. But as you move deeper, densities soar. At some critical point, neutrons may break down into quarks, producing quark matter in the core. Normally, when matter undergoes such a drastic change, the star's structure changes too. It gets smaller, heavier, or unstable. But in the twin star scenario, the star can reach a first-order phase transition, where matter suddenly flips from one phase to another, like water freezing into ice. Both phases, ordinary neutron matter and quark matter, can support stars of the same mass, but with different internal compositions. In this case, one of the stars could be a pure neutron star, held together by the well-known nuclear forces, but its twin would be a combination star, with a core made of quarks and a shell made of neutron matter. From the outside, they would look the same. They'd both spin at the same speed and weigh the same. But what was inside them would make them very different animals. Why does this matter? Because it could solve some long-standing puzzles. For example, astrophysicists have observed neutron stars with very different radii despite having similar masses. Some appear puffier with larger radii, while others look more compact. If twin stars exist, then both could weigh, say, 1.9 solar masses, but one could be several kilometers larger across. That difference might reflect whether the star has transitioned into a quark core. The twin star hypothesis also ties directly to gravitational waves. When neutron stars merge, the way they deform and the signals they produce depend strongly on their inner structures. If two twin stars collided, one a neutron star, the other a hybrid star, the resulting gravitational wave could carry fingerprints of their differences. By carefully analyzing those signals, scientists could detect the telltale signature of a hidden quark core. Events like GW 170817, the famous 2017 neutron star merger, have already given tantalizing hints. Some interpretations suggest that at least one of the colliding stars may have contained exotic matter, though the evidence isn't yet conclusive. The link between twin stars and the mass-radius relation is another interesting thing about them. If you put all the known neutron stars on a graph of mass versus radius, they should all fall along a smooth curve, right? But twin stars would make a second group of stable arrangements. The line would have a fork shape because stars with the same mass could show up at two different distances. Finding this fork would be proof of strange phase changes happening inside neutron stars. This is exactly what instruments like NASA's NICA camera are made to do. They look at X-rays to measure the size and shape of pulsars. Early data has already shown that not all neutron stars fit nicely onto one shape. This means that twins are still possible. There are also possible implications for pulsar glitches, sudden tiny changes in rotation speed. If a neutron star suddenly transitions into a twin configuration, releasing energy as its core changes phase, that could trigger a glitch-like event. The fact that pulsars sometimes behave unpredictably may hint that some are on the brink of becoming twins. The glitching core. Neutron stars have a strange habit of speeding up all of a sudden, with no notice. Imagine a star that is only 20 kilometers across, weighs more than the Sun, and spins hundreds of times per second with the accuracy of a machine. In an instant, that perfect beat breaks. The star's speed jumps forward by a very small amount, like a cosmic hiccup. Pulsar glitches are some of the best proof that the cores of neutron stars hide physics that can't be found anywhere else in the universe. To grasp the puzzle, start with how pulsars normally work. Pulsars are neutron stars that shoot beams of radiation from their poles, acting like cosmic lighthouses. As they spin, the beams sweep across Earth, and we detect regular pulses, often accurate to within a fraction of a microsecond. They're so precise that astronomers have compared them to atomic clocks, yet every so often, that clock skips. The pulsar spins faster than before, then slowly relaxes back to its previous rate. These glitches can happen in a blink, and they hint at something dramatic happening deep inside the star. The leading explanation involves superfluid neutrons in the core. A superfluid is a bizarre state of matter that flows without friction. On Earth, scientists have created superfluids from liquid helium, which can creep up walls or flow endlessly through tiny cracks. Inside a neutron star, conditions are perfect for neutrons to enter a superfluid state. But unlike normal fluids, a superfluid can't spin freely. Instead, it forms tiny whirlpools called vortices, which lock into place like invisible gears controlling the star's rotation. As the outer crust of the neutron star slows down due to magnetic braking, the superfluid inside keeps spinning faster. Tension builds. Then, in an instant, vortices snap loose and transfer their momentum to the crust. The result? The entire star suddenly speeds up, producing the observed glitch. It's as if the star has an inner motor that occasionally kicks in and gives it a jolt. But this simple picture hides a lot of secrets. One thing is that not every glitch looks the same. Some are very big and make the star stand out, while others are very small and hard to see. Some stars fail a lot, while others don't have an event in decades. About 1,000 light-years away, the famous Vela pulsar is known for big problems that happen regularly, about every 3 years. The Crab pulsar, on the other hand, glitches less often and has smaller jumps. What's the difference? It's possible that the shape of the core and the way the superfluid interacts with the crust may be different in each star. There's also the puzzle of what happens after a glitch. Typically, the pulsar doesn't keep spinning faster forever. Instead, it relaxes back toward its previous rate over days, weeks, or months. This recovery suggests a slow recoupling between the superfluid interior and the crust. The details of that relaxation carry clues about how matter flows and interacts at extreme densities. By studying the post-glitch behavior, scientists can test different models of superfluidity inside neutron stars. In fact, the idea that glitches could show quantum mechanics on a stellar size is even more intriguing. Vortices and superfluids are quantum events that usually only happen in labs and very small systems. They spread out over 20-kilometer-wide objects, with more mass than the Sun, though, in neutron stars. Every bug we find is like a big quantum physics experiment that teaches us something new about how these strange rules work in the harshest conditions. Other experts have also come up with other theories. As an example, the star's magnetic field could quickly change directions, causing changes in the crust's pressures and what is known as a starquake. The quick change in form could cause angular momentum to be redistributed, which would make the star spin faster. Others say that when the star's limits change, glitches might be caused by interactions between different layers, like the outer neutron superfluid and an inner quark matter core. In recent years, new glitches have been observed by instruments like NICA aboard the International Space Station. NICA measures X-rays from pulsars with high precision, providing additional information beyond timing alone. Combining radio and X-ray observations lets scientists cross-check how the glitch affects both the star's rotation and its surface hotspots. Gravitational waves could even be used one day. Bugs that cause quick changes in the structure of matter inside the star could cause small waves in spacetime. So far, no problem has been linked to a gravitational wave, but in the future, monitors may be able to pick one up. That would give us a whole new way to look into the glitching core. The magnetic monster effect. Though neutron stars are already very strange, a very small number of them make them even stranger. There are neutron stars called magnetars out there that have magnetic fields so strong that they could erase a credit card from the other side of the moon. Their fields are trillions of times stronger than Earth's. They are strong enough to bend spacetime, warp atoms, and maybe even change the shape of the matter inside their cores. This is where the magnetic monster effect comes in. This is the idea that magnetic fields don't just sit on the outside of magnetars. They go deep into the heart and change the way matter acts. Magnetars were first proposed in the 1990s to explain mysterious bursts of high-energy radiation. Unlike normal pulsars, which emit steady beams of radio waves or X-rays, magnetars erupt unpredictably, releasing more energy in a second than our Sun produces in 100,000 years. These bursts hint at colossal stresses inside the star, stresses that are somehow linked to the ultra-strong magnetic field. But while the eruptions are visible on the outside, the real mystery lies on the inside. In normal neutron stars, matter is already squeezed to unimaginable densities. Neutrons pack so tightly that a teaspoon of material would weigh billions of tons. Inside, superfluids and superconductors may exist, flowing and conducting electricity in strange, frictionless ways. But when you add magnetic fields into the mix, things get far more complicated. In a magnetar, the field can reach strengths of 10-15 Gauss, enough to dominate the physics of the core itself. How does this kind of magnetic field affect neutrons that are superfluid? This is a big question. A superfluid usually moves without any problems, but strong magnetic fields might mess up the tiny quantum vortices that make it possible for it to spin. Imagine an unseen barbed wire suddenly running through a fluid that doesn't stick to anything. This could cause extra stress to build up over time until it explodes in a gigantic way as a magnetic flare or starquake. These things might explain why magnetars sometimes send out huge flares that can be seen from galaxies away. The magnetic field could also alter the behavior of protons and electrons in the core. In ordinary neutron stars, these charged particles may form a superconducting fluid, allowing electric currents to flow without resistance. But under a trillion Gauss field, superconductivity may break down or change into a new exotic state. Some theorists suggest that color superconductivity, a state where quarks themselves pair up into superconducting forms, might appear or disappear depending on magnetic strength. In this way, the core of a magnetar could cycle through different phases of matter, driven not by density or temperature, but by magnetic stress. The magnetic monster effect also has consequences for the star's stability. Normally, neutron stars balance gravity's inward pull with the outward pressure of dense matter, but a strong magnetic field can provide extra support or destabilize the structure, depending on its configuration. If the field is tangled or uneven, it may push on the star unevenly, leading to cracking of the crust or sudden shifts in the interior. These shifts could trigger the observed bursts and starquakes that make magnetars so violent. What has been seen supports this. Magnetars like SGR 180620 have sent out huge flares that were so strong that they changed Earth's top atmosphere for a short time, even though they are 50,000 light-years away. The energy that was released shows that the star's magnetic fields quickly changed places inside it, moving stress from the center to the surface. The shaking motion might also cause movements inside the star, which would lead to quasi-periodic oscillations, which are the regular patterns seen in X-ray afterglows. It's possible that these rhythms are direct signs of how matter acts when a trillion Gauss field shakes it. Magnetic fields also affect how neutron stars merge. When two magnetars or a magnetar and a neutron star collide, the fields can interact violently, twisting spacetime and potentially boosting the resulting gravitational wave signal. Some researchers suspect that short gamma-ray bursts, some of the most powerful explosions in the universe, may be fueled by the release of magnetic energy in these mergers. If so, then the magnetic monster effect isn't just a curiosity. It's a key driver of cosmic fireworks visible across billions of light-years. The magnetic monster effect might be most interesting because it could change the line between neutron stars and black holes. A magnetar might be able to hold more mass than a normal neutron star because it has a stronger magnetic field that keeps it from collapsing. On the other hand, magnetic stress could make matter less stable more quickly, which would cause stars to fall earlier than thought. In either case, magnetars make science rethink where the limit is and what strange states of matter can happen before gravity takes over. Phase transitions in the heart. Inside a neutron star's core, matter is pushed to limits that don't exist anywhere else in the universe. The pressures are so extreme that even the strongest forces known in physics, the ones binding protons and neutrons together, may buckle. When that happens, the material doesn't just change gradually. It could undergo a phase transition, flipping into a completely different state of matter, much like water suddenly freezing into ice or boiling into steam. But in neutron stars, these changes happen at densities billions of times greater than anything we can create on Earth, and the transitions may hold the key to what these stars really are. A phase transition means that matter reaches a tipping point. For example, in everyday life, water remains liquid as you cool it, but at 0 degrees Celsius, it changes all at once into ice. In neutron stars, the same kind of tipping point may exist, only the ingredients are neutrons, protons, quarks, and possibly exotic particles. The heart of the star may flip from one phase to another, creating sharp boundaries deep inside. Scientists think these transitions could explain many strange neutron star behaviors, from their masses and radii to their sudden glitches, and even the way they merge. The change from neutron matter to quark matter is one of the ones that scientists study the most. Neutrons stay whole at low densities, making a sea of particles that are squished together but can still be seen. But when there are more neutrons in a space, they may break apart into quarks, which are their building blocks. If this happens all of a sudden, it makes a clear core within a core, a line between normal neutron matter and free quark matter. This inner core would act in a very different way, which would change how the star cools, spins, and sends out neutrinos. Some scientists think that these kinds of changes could create hybrid stars, which are somewhere between neutron stars and something completely new, called quark stars. Another candidate transition involves hyperons, strange cousins of protons and neutrons that contain unusual quarks. Models predict that hyperons could appear when pressure crosses a critical threshold. But their arrival complicates things. Hyperons are heavier and reduce the pressure support inside the star, making it easier for gravity to collapse the star into a black hole. If a sudden wave of hyperons forms, it could destabilize the star instantly. Yet puzzlingly, we've observed neutron stars heavier than two suns that are still stable. This suggests that either hyperons don't appear, or the transition behaves in unexpected ways. Phase transitions could also involve meson condensates, exotic forms of matter where particles like kaons or pions clump together in strange quantum states. These condensates, if they exist, would alter the way the core handles pressure and cooling. For instance, a pion condensate might speed up neutrino production, draining energy from the star much faster than expected. This could explain why some neutron stars cool at surprising rates. The hard part is figuring out whether these changes are smooth or sudden. If they are smooth, the star's qualities would change slowly as it got denser, which would make them harder to find. The star could change states, though, if the changes are sudden, like when water freezes. Jumps like these could even lead to terrible things happening. For instance, a neutron star that all of a sudden changes into a quark core phase might get a little smaller, which would release a lot of energy. Some scientists think that these events might cause gamma-ray bursts or strange signs in gravity waves. Gravitational wave astronomy has given us our first chance to test these ideas. When two neutron stars collide, the gravitational waves they emit depend strongly on how squishy the stars are. If phase transitions occur, then stars of the same mass could behave differently in a merger. One resisting collapse longer, another caving in sooner. The 2017 event GW 170817 gave us hints that something like this may be happening, though the data wasn't clear enough to prove it. Future detectors, with sharper sensitivity, might catch the telltale fingerprints of a phase change in the heart of merging stars. Another clue may come from twin star models. As described earlier, the existence of two neutron stars with the same mass but different radii could be a direct sign of phase transitions. The smaller one could have flipped into an exotic phase, while the larger one stayed in the normal phase. Finding this split in the population of neutron stars would be strong evidence that sharp internal boundaries really exist. Phase changes are even more remarkable because they blur the line between particle physics and astronomy. The same questions that are being studied in neutron stars, how matter acts at very high densities, are also being tried in huge reactors on Earth, such as the Large Hadron Collider. Scientists can make tiny, short-lived drops of quark glue on plasma by smashing heavy ions together. But in neutron stars, those drops could stay put and fill up whole cores. Accelerators might not be able to reach the answers that these stars' phase changes hold. The neutrino factory. Neutron stars are already some of the strangest objects in the cosmos, but their cores may also double as cosmic factories for neutrinos, ghostly particles that zip through matter as if it isn't even there. Neutrinos are produced in abundance in supernova explosions, but neutron stars keep making them long after their birth. In fact, one of the biggest mysteries in astrophysics is why some neutron stars cool so quickly, and the answer may lie in their ability to churn out unimaginable numbers of neutrinos from their dense hearts. To understand why this matters, remember that a newborn neutron star is blisteringly hot, with internal temperatures reaching hundreds of billions of degrees. Over time, the star cools, radiating away heat. But instead of losing most of its energy as light or X-rays, it mainly sheds heat through neutrinos. Unlike photons, which can bounce around and get trapped, neutrinos pass almost unhindered through dense matter. Once produced in the core, they stream out almost instantly, carrying energy away like invisible messengers. The question is, how are these neutrinos being made? The most basic process is called the Urca process, named after a casino in Brazil, because like money disappearing at the roulette table, energy seems to vanish rapidly through neutrinos. In this process, neutrons, protons, and electrons inside the core constantly interact. A neutron can turn into a proton and electron while releasing a neutrino, or the reverse can happen. Each reaction produces a stream of neutrinos that quickly escape. In dense environments, this cycling can run at incredible rates, creating a near-constant neutrino wind. But this simple model isn't enough to explain all the cooling behavior we see. Some neutron stars cool at a steady pace, while others seem to cool far faster than theory predicts. For instance, observations of the neutron star in the supernova remnant Cassiopeia A revealed that its temperature dropped sharply over just a decade. This dramatic cooling hinted at something special happening deep inside its core. The leading theory? That superfluid neutrons were forming, releasing bursts of neutrinos as they paired up into quantum states. Essentially, the star's interior was rearranging itself, and neutrinos were the byproduct of the transformation. Neutrinos could also be made more quickly through other strange processes. It's possible that hyperons or kaons could make new processes possible inside the core, which would make neutrinos come out even faster. The core would become an even better neutrino generator thanks to these pathways, which are sometimes called direct Urca processes. The catch is that these kinds of reactions need the right amount of protons and neutrons, and we don't know if most stars have that amount yet. It's possible that strange neutrino routes are at work though, since some stars cool down a lot faster than others. Neutrino factories are also linked to the idea that stars go through phase changes. Matter could release a lot of neutrinos if it changes from being mostly neutrons to being mostly quarks, or if meson condensates form. Not only might these bursts quickly cool the star, but they might also send out signs that we can see if we're lucky enough to catch one. It would be a once-in-a-lifetime event for astrophysics to find such a neutrino burst coming from a close neutron star. It would give us a straight look into the core's hidden processes. In magnetos, the intense fields could affect how neutrinos escape, bending their paths or changing their production rates. Some models suggest that strong fields might even polarize neutrinos, aligning their spins in unusual ways. This could leave imprints on the cooling patterns of magnetars, making them distinct from normal neutron stars. The neutrino story also ties directly into supernovae. When a massive star collapses, more than 99% of the explosion's energy escapes as neutrinos. Detectors on Earth, like superconductivity in Japan, have caught neutrinos from supernova 1987A, confirming that they play a central role. But in neutron stars, the factory keeps running for tens of thousands of years. If we could catch even a fraction of those neutrinos, we could test theories about what's happening deep inside. Unfortunately, neutrinos interact so weakly that even massive detectors buried underground only catch a handful during rare nearby events. The mystery of maximum density. Matter has to reach its end point at some point. A certain point is reached when things refuse to be pushed any further. This is easy to see on Earth. If you crush a rock, you get dust. If you squeeze atoms, the electrons don't want to fall into the center. But in neutron stars, nature goes beyond what we know. We still don't know if matter has a true maximum density, or if the universe lets it keep getting denser and denser until only a black hole is left. Neutron stars are so strange that we don't really understand how they work. A neutron star is born when a massive star collapses after a supernova explosion. Gravity crushes the core until protons and electrons combine into neutrons, leaving behind an object smaller than a city but heavier than the Sun. In these conditions, neutrons themselves are squeezed shoulder to shoulder. The density in the inner core can reach several times that of atomic nuclei, the densest stable matter we know on Earth. But what happens beyond that is unknown. A possible explanation is that there is a real limit to how much something can be compressed. This idea says that once neutrons hit a certain density, they can't be squished closer together because the forces inside quarks, which are what neutrons are made of, don't let them go any further. This means that density comes to a hard stop, and if gravity pushes harder, the star falls into a black hole. With this theory, the universe is clearly split into two groups: neutron stars that are below the limit of density, and black holes that are above it. Some scientists think that neutrons may not resist forever. Instead, they may break apart under extreme pressure, releasing their quark building blocks. In this scenario, the density doesn't stop, it simply changes form. Instead of a maximum density, you get quark matter, a new phase where quarks roam freely instead of being trapped inside neutrons. If true, then the center of a neutron star isn't defined by a hard maximum density, but by a transformation into something stranger. This question is tied closely to the equation of state, the relationship between pressure and density inside neutron stars. A stiff equation of state means matter resists compression strongly, leading to larger, puffier stars. A soft equation means matter yields more easily, creating smaller, denser stars. Observations of neutron star masses and radii hint at which equations might be correct, but the data so far is murky. Some stars appear unusually massive, suggesting matter resists collapse more than expected. Others appear tiny, hinting at greater compressibility. The lack of a single answer may be because different stars reach different phases of matter, depending on their density. There's also the possibility that matter can go beyond quarks. Some physicists propose the existence of strange quark matter, where quarks arrange themselves into even denser, more stable states. If this exists, then the maximum density isn't a barrier, but a gateway to a new kind of star, a strange star. In that case, neutron stars might naturally transform once they cross a certain density threshold, leaving no sharp dividing line at all. To test these ideas, scientists look to phenomena like gravitational waves from neutron star mergers. When two stars spiral together and collide, the way they deform under pressure encodes information about their maximum density. If matter is stiff and resistant, the stars bounce and wobble differently than if matter is soft and easily compressed. The landmark event GW 170817 gave tantalizing hints, but not yet a definitive answer. Future detectors may reveal whether there's a universal density ceiling or a smooth slide into exotic states. Events that cool down quickly give us another sign. If the core's density is high enough to allow direct quark interactions or unusual condensates, those processes would send out a lot of neutrinos, which would quickly cool down the star. For example, the neutron star in Cassiopeia. A cooled down a lot faster than anyone thought it would. This could mean that its core density moved into a new range where unusual particles are more common. Strange quark matter. There are many strange ideas about what's inside a neutron star, but one that is both scary and interesting is the idea that its core is made of strange quark matter. This is not science fiction, it's a real idea that scientists are looking into. What if neutron stars aren't made of neutrons at all? They might be made of a new kind of matter that is more stable than anything else in the universe. Even more amazing is the idea that weird quark matter could spread like a virus and change whole stars into what are sometimes called strange stars. To understand the idea, start with quarks. Quarks are the building blocks of protons and neutrons, and they come in 6 flavors: up, down, strange, charm, top, and bottom. Everyday matter, the atoms in your body, the air, and the earth, is made of just 2 flavors: up and down quarks. Neutrons are made of 1 up and 2 downs. Protons are 2 ups and 1 down. But what happens if you squeeze matter so tightly that these protons and neutrons fall apart? At the densities inside neutron stars, some physicists think this happens. The quarks could break free, creating a soup of quark matter. Normally, you'd expect this soup to be made only of up and down quarks, since that's what we start with. But under extreme pressure, strange quarks may join the mix, creating a blend of up, down, and strange quarks. This combination is called strange quark matter. Why is this important? Because strange quark matter might actually be more stable than ordinary matter. That means that, under the right conditions, once strange quarks appear, they don't go away, they stay. A neutron star could then naturally shift into a strange star, with its entire interior made of this exotic stuff. Several researchers think that if a very small amount of strange quark matter, which is sometimes just called a strangelet, touched regular matter, it could turn it into strange matter too. neutron matter would slowly change into strange matter as this reaction spreads like a chain reaction. This idea sounds very scary, but it's not backed up by any clear proof and is heavily debated. It has kept scientists up at night though, because if it's true, strange matter could someday eat whole stars. Strange stars would look a lot like neutron stars from the outside. They'd still be small, dense, and spin rapidly, but their interiors would behave differently. For example, strange stars might have slightly smaller radii for the same mass, because strange matter can be packed more tightly. They might also cool faster, since strange quark interactions produce neutrinos more efficiently. Some unusual cooling observations have made scientists wonder if certain neutron stars are secretly strange stars in disguise. There's also the idea that strange quark matter might be the true ground state of matter, the lowest possible energy configuration. If this is correct, then all ordinary matter is only metastable, meaning it could transform into strange matter under the right conditions. In this view, neutron stars aren't strange exceptions. They're just the first step toward a universe where strange matter eventually dominates. Particle accelerators on Earth have even tried to create strange quark matter by smashing heavy nuclei together. So far, no stable strangelets have been found, but the experiments aren't conclusive. The energies and pressures inside neutron stars are far beyond anything we can replicate in a lab. If strange matter does exist, we may only ever detect it indirectly, through the astrophysical signatures of stars that behave unlike ordinary neutron stars. A neutron star could suddenly change into a strange star, which is one of the most exciting options. Strange quarks might show up if the core reaches the right density. The change could spread outward and change the whole star in seconds. This would let out a huge amount of energy, which could lead to a gamma-ray burst or some other high-energy signal. Some scientists think that mysterious bursts in the universe could be neutron stars changing into strange stars. Pion condensates. There are conditions inside the core of a neutron star that are so harsh on matter that they start to break the rules of normal particle physics. One of the strangest things scientists have thought about is the creation of Pion condensates, which are strange groups of particles called pions. If this is true, it means that the center of a neutron star doesn't just have neutrons and quarks, it also has pions, which control the physics in ways we can't fully understand yet. So what exactly are pions? In the simplest sense, they are particles that act as messengers of the strong nuclear force, the force that holds atomic nuclei together. On Earth, pions are short-lived, created in high-energy collisions inside particle accelerators or cosmic ray showers in the atmosphere. They decay within a fraction of a second. But in the extreme density of a neutron star, conditions might allow pions not just to appear, but to stick around and form a collective state similar to a Bose-Einstein condensate. A Bose-Einstein condensate is a state of matter where many particles collapse into the same quantum state, acting as if they were a single superparticle. Normally, this happens at extremely low temperatures, such as with ultracold atoms in a laboratory. But inside a neutron star, it could happen because of the immense density and pressure. Instead of atoms, it would be pions that all align into a shared coherent state, a pion condensate. Why would pions appear in the first place? Inside neutron stars, the balance of protons, neutrons, and electrons is delicate. At extreme pressures, neutrons can decay into protons and electrons, releasing neutrinos in the process. The presence of these protons and electrons can allow charged pions to form. If enough pions are produced, and the conditions are right, they may stop behaving like individual particles, and instead merge into this exotic condensate state. This kind of vapor would have a huge effect. One thing that would change is how the star makes neutrinos. It is easier for the star to make neutrinos and lose heat because pion condensates open up completely new reaction pathways. This might be the reason why some neutron stars cool down a lot faster than expected. Their cores could be full of pions giving off energy. Since many years, no one has been able to figure out why the neutron star in Cassiopeia A is cooling. One possible reason is Pion condensation. This would also change the star's health and the largest amount of matter it can hold. When pions compact, they soften the star's equation of state, which makes it easier for matter to get smaller. This would make it possible for a neutron star to have less mass before it turns into a black hole. Particle condensates might be like a weight limit for neutron stars, deciding which ones stay stars and which ones turn into black holes. Neutron stars that are very heavy seem to go against this idea. But it's possible that only stars in the right density range form condensates. Magnetic fields could complicate the story even further. In magnetars, where fields are trillions of times stronger than Earth's, pions might align differently, creating anisotropic condensates that behave differently depending on direction. This would make the physics even stranger, potentially affecting how magnetars release bursts of X-rays and gamma rays. Some models suggest that sudden rearrangements of Pion condensates could even power violent starquakes or explosive flares. The Pion condensate idea also connects to the broader family of meson condensates. Just as pions might condense, other mesons like kaons have been proposed to do the same under extreme conditions. Both would signal that neutron stars aren't just made of baryons like protons and neutrons, but also of these force-carrying particles acting in collective states. If true, this would mean neutron star cores are playgrounds for quantum field theories in action, testing ideas far beyond what Earth labs can achieve. For the most part, nuclear physics calculations show that pion condensation is possible when densities are higher than about twice those of atomic nuclei. But these estimates rely on factors that aren't always clear, like how nuclear symmetry energy behaves and how dense matter interacts with itself in very harsh conditions. There are models that strongly support pion condensates and models that completely rule them out. No one agrees on anything, which shows how strange neutron star cores are. If pion condensates do exist, they could also have cosmic scale consequences. For example, in neutron star mergers, the presence of condensates could change the dynamics of the collision. The gravitational wave signals we detect would carry subtle imprints of how easily matter compresses and flows. Comparing data from different mergers might reveal whether condensates are at play. Similarly, sudden shifts in condensate structure might power bursts of radiation we don't yet fully understand. The three-layer puzzle. Neutron stars are often explained with a simple model: 3 layers stacked on top of each other like an onion. The crust is the first layer. It is a thin but very thick shell. The upper core, which is below that, is mostly made up of neutrons. The inner core is in the middle. It's a strange place where the rules of physics may change into something we've never seen before. For decades, this 3-layer picture has been used as a guide. These neat ideas start to fall apart, though, as we learn more about neutron stars. It's possible that the truth is much weirder than a neat split into 3 layers. Let's start with the crust. Even this thin layer, only about a kilometer thick, is extreme beyond imagination. It's often compared to a giant crystal lattice, where nuclei are packed together more tightly than anything we can create in a lab. Electrons zip freely through this crust, making it electrically conductive and rigid. But even here, weird phases of matter appear. Near the bottom of the crust, particles begin forming bizarre nuclear pasta shapes, spaghetti-like filaments and lasagna-like sheets. This blurs the boundary between crust and core. Is it really a clean separation, or is it already the start of the next layer? Next comes the outer core, a region believed to be mostly neutrons with a small fraction of protons and electrons. Some models suggest that neutrons in this region behave as a superfluid, flowing without friction. Protons may act as a superconductor, carrying electric current without resistance. Together, these phases could explain certain strange behaviors of pulsars, such as sudden jumps in their rotation rate. But the outer core might not be uniform at all. Instead, it could contain pockets of exotic particles, hyperons, mesons, or even free quarks. If so, the line between outer and inner core becomes fuzzy, not a sharp boundary. Finally, there's the inner core, the most mysterious of all. In the classic three-layer model, this is where matter is compressed to densities many times higher than atomic nuclei. But what actually lives here is hotly debated. Some theories say it's still neutrons, just even more tightly packed. Others argue that quarks roam free, forming a quark soup. Still others suggest even stranger possibilities like condensates of pions or kaons, or even more exotic states such as strange quark matter. The truth could involve multiple phases stacked on top of each other, with sharp boundaries or smooth transitions. The problem with the three-layer picture is that it assumes neat divisions, like floors in a building. But in reality, nature rarely works that way. Transitions between different phases of matter may be gradual, overlapping, or mixed. Just as water can exist as slushy ice and liquid at once, neutron star matter may exist in hybrid states that defy clean labels. For example, the crust core boundary may be filled with tangled regions of nuclear pasta, blurring the separation. The outer and inner core might blend, with pockets of quark matter existing alongside neutron-rich zones. Observations are beginning to show how complicated these issues are. For example, research into gravity waves from neutron star mergers shows that stars change shape in different ways based on how easily their insides can be compressed. There are models that work better with a hard core and models that work better with a soft, easily collapsible core. It seems that neutron stars might not all have the same three-layer pattern, since different models don't always fit the data. Instead, the mass, age, or magnetic field of a star could make its core structure very different from one star to the next. The three-layer model also struggles to explain certain phenomena like star quakes. These sudden jolts in neutron stars release massive amounts of energy, suggesting that their interiors store stress in complex ways. A simple three-layer onion doesn't capture how magnetic fields, superfluid vortices, and condensates all interact deep inside. Similarly, rapid cooling in some stars hints that exotic particles are carrying energy away more efficiently than the basic model allows. Observations in the future might help solve the mystery. The NICER camera, which studies X-rays coming from hotspots on the surfaces of neutron stars for NASA, is already getting closer to finding out how big these stars are. Gravitational wave sensors are giving us hints about how neutron stars change shape when they crash into each other. Neutrino monitors might one day show if strange particles like pions or kaons play a part inside. With each piece of information, we'll see if the three-layer picture stays together or falls apart under the weight of its own complexity. Gravitational waves as probes. Neutron stars seemed like something we could only study indirectly for a long time. Not close enough to touch, too thick to copy in the lab, and too strange for even the most powerful binoculars to see through. Things changed in 2015, though. For the first time, scientists have found gravitational waves, which are ripples in space-time, caused by heavy things moving very quickly. We now have a whole new way to look into the hearts of neutron stars thanks to this big step forward. All of a sudden, these waves turned into probes that could find out things about matter at levels we had never thought possible. When two neutron stars orbit each other in a binary system, they spiral inward as they lose energy to gravitational waves. As they get closer, the stars begin to distort each other. They aren't perfectly rigid spheres. Instead, each neutron star stretches slightly under the gravitational pull of the other, like a rubber ball being squeezed. These tiny deformations affect the exact shape of the gravitational wave signal. Scientists call this effect tidal deformability. By carefully analyzing the ripples, researchers can figure out how stiff or soft neutron star matter really is. This stiffness directly relates to the equation of state, the rulebook that describes how matter behaves under extreme pressure. If neutron star matter is very stiff, the stars resist deformation and remain puffed up. If it's soft, they shrink more easily under pressure. Different models of what lives inside neutron star cores, neutrons, hyperons, quarks, or exotic condensates, predict different stiffness levels. So every gravitational wave detection is like a cosmic fingerprint, narrowing down which models fit reality and which don't. GW170817, which was found in August 2017, was the event that showed this method works. It was proven to be the first time that two neutron stars came together. The signal told them about the stars' sizes, masses, and how easily they could be pushed around by tides. Scientists were able to connect the science of the core to real blasts in the universe by looking at a bright flash of kilonova radiation through telescopes. Light waves and gravitational waves work together to give us a fuller picture. This was the start of multi-messenger astronomy. Since then, gravitational wave observatories like LIGO, Virgo, and Kagra have been listening for more neutron star collisions. Each new event adds another data point. With dozens of detections expected in the coming years, scientists hope to build a catalogue of signals that reveal a spectrum of neutron star behaviors. Some collisions might involve stars with very different masses, or even a neutron star merging with a black hole. Each scenario tests the physics of dense matter in unique ways. Finding signs after a merger is another interesting option. When two neutron stars hit each other, they don't always turn into black holes right away. They can sometimes join together to make a hypermassive neutron star that lasts for seconds or even milliseconds. As long as it's alive, it moves very strongly, sending out higher frequency gravity waves. Those signs might help us understand how matter acts right on the edge of collapsing. So far, post-merger signs have been too weak to be sure of, but in the future, devices that are more sensitive might be able to pick them up. Gravitational waves may also reveal whether exotic particles like hyperons or quarks actually exist. If such particles soften the equation of state, then stars should leave specific imprints on the waveform before they collide. For example, stars containing quark matter might squish more dramatically, changing the timing and strength of the final signal. By comparing real signals to simulated ones, scientists can test which kinds of matter are consistent with the data. Looking even further ahead, the next wave of telescopes, like the Einstein telescope in Europe and the Cosmic Explorer in the US, will make this field much bigger. They will be sensitive enough to find neutron star collisions billions of light years away, not just close to where we are in the galaxy. With that much power, we can make a picture of how neutron stars have behaved throughout the past of the universe and see if their insides have changed or stayed the same over time. NICE's X-ray mapping. You can't just point a regular telescope at a neutron star and look inside it. Even the most powerful telescopes can only make out these stars as tiny dots because they are so far away and small. Also, you can look at their X-rays for another way. That is where the NICE project from NASA comes in. Neutron Star Interior Composition Explorer, or NICE, is the name of the camera that is on the International Space Station. Its only job is to study neutron stars by looking at the X-rays they give off. Scientists use NICE to turn neutron stars from strange points of light into precise maps that show their size, mass, and even the structure of their surfaces. So, how does it work? Neutron stars are extreme remnants of collapsed stars, and many of them are pulsars. They spin rapidly, beaming out radiation like cosmic lighthouses. As these stars rotate, hotspots on their surfaces send bursts of X-rays toward Earth. NICE captures these flashes with incredible precision, down to microseconds. By studying how the X-rays brighten and fade as the star spins, scientists can build models of the star's shape, size, and gravitational field. In other words, NICE turns flickering light into a map of the star's interior physics. One of NICE's greatest achievements has been measuring the radius of neutron stars with unprecedented accuracy. Before NICE, scientists could only estimate radii based on indirect signals, and the uncertainty was huge. With NICE, the hotspots on pulsars act like natural rulers. By modeling how the X-rays bend around the star due to gravity, scientists can determine the star's size. Combining this with mass measurements from pulsar timing allows them to narrow down the equation of state, the key relationship that describes how matter behaves at extreme densities. A good example is NICE's study of PSR J0030 plus 0451, a millisecond pulsar about 1,100 light-years away. NICE's observations revealed that this neutron star has a radius of about 13 kilometers. But the most surprising part was its hotspot pattern. Instead of having simple circular hotspots near the poles, the star showed two oddly shaped hotspots, one crescent-shaped and one patchy. This challenged the standard picture of pulsar magnetic fields and hinted that neutron stars may have far more complex surface structures than expected. These shapes also affect how X-rays escape, which in turn provides clues about the star's dense interior. NICE's precision has also helped in testing the limits of neutron star masses. By measuring both mass and radius for the same star, scientists can rule out certain exotic matter models. For example, some equations of state predict stars that are too soft, meaning they can't support heavy neutron stars above 2 solar masses. NICE's data, combined with radio and gravitational wave observations, has shown that neutron stars can indeed reach those heavyweights. That immediately rules out many models that relied heavily on exotic particles like hyperons softening the star too much. But NICE isn't only about structure, it also sheds light on how neutron stars behave in real time. By monitoring X-ray bursts from accreting neutron stars, those pulling matter from a companion star, NICE can watch how matter behaves under crushing pressure as it slams onto the surface. These bursts often involve thermonuclear explosions that cover the entire star, releasing huge amounts of X-rays. The patterns and energy from these events give another angle on what lies beneath the surface, since the crust and core must respond to such violent outbursts. NICE's data can be compared with gravity wave finds, which is one of the coolest things it can do. NICE checks how neutron stars look when they are not interacting with anything else. Gravitational waves check how they change shape when they crash into each other. It gives people more faith in the models if both of them point to the same hardness for the matter inside. If they disagree, it means that something strange is going on. For example, there could be strange stages like quark matter or meson condensates. In this way, NICE and other telescopes work together to find out more about the universe. Neutron stars may not have smooth sides at all, which is another interesting finding. Based on NICE's data, hotspots may be uneven, curved, and spread out in odd places. They are important because they change how the light moves around the star. It means the star is smaller and heavier if gravity bends light more than expected. The star might be bigger if it bends less. By getting better at these readings, NICE keeps working on one of the biggest puzzles in astrophysics: how dense matter really is. The number of neutron stars whose sizes can be accurately estimated will grow as NICE continues to look at them. Every one of them completes the picture. Some may show stars that are bigger than predicted, which could mean that the equations of state are stronger. Some may be smaller, which suggests that the matter is lighter and lets strange particles show up. The end goal is to make a map of different neutron star structures so that we can be sure that their cores are made of neutrons and nothing else. Massive star outliers. For many years, experts thought they knew a lot about how heavy neutron stars are. A tight range of about 1.2 to 1.5 times the mass of our Sun was used to measure most of them. This made sense. Neutron stars are made when big stars explode as supernovae, and the way they collapsed seemed to organize their masses into a range that could be predicted. Then there were the outliers, neutron stars that were so massive that they didn't follow the rules. This made scientists rethink what's possible inside these star remains. PSR J0740 plus 6620, a pulsar that weighs about 2.1 solar masses, is one of the most well-known types. That is almost 40% heavier than the old neutron star that was thought to be normal. That much mass, packed into such a small place, is amazing for something that is only 12-13 kilometers across. It's a big question how a neutron star with such a high mass can stay together and not collapse into a black hole. The answer lies in the strange stuff that's inside them. In physics, the maximum mass of a neutron star depends on the equation of state, the rules describing how dense matter resists gravity. A soft equation of state means matter squishes easily, limiting the star's maximum mass. A stiff equation of state means matter pushes back harder, allowing heavier stars to stay stable. The problem is, many popular models that included exotic particles like hyperons or mesons predicted stars would collapse long before reaching 2 solar masses. Yet the outliers clearly exist. That suggests either our understanding of exotic matter is wrong, or something about neutron star cores makes them much stiffer than expected. The fact that these huge neutron stars exist also makes us wonder how they are made. Normal models of supernovae don't easily leave behind such heavy debris. It's possible that some neutron stars get more mass over time by taking matter from a nearby star. As time goes on, regular accretion could push a star over the 2 solar mass limit. Another idea is that some very massive stars in low metallicity settings, places with few heavy elements, can directly make heavier neutron star cores when they crash. There may be more than one way for a neutron star to live its life, as shown by both of these situations. These outliers also link directly to gravitational wave astronomy. When 2 neutron stars merge, the total mass of the system determines whether the result collapses immediately into a black hole or briefly survives as a hypermassive neutron star. The discovery of very heavy neutron stars means nature can push the limits further than expected, affecting how we interpret merger signals. In fact, analyzing the aftermath of gravitational wave events has already provided independent evidence that some neutron stars must have maximum masses above 2 solar masses. What makes the outliers especially exciting is how they challenge exotic matter theories. For instance, models that include hyperons, strange cousins of protons and neutrons, predict that neutron stars should collapse earlier because hyperons soften the equation of state. But the 2 solar mass stars seem to survive just fine, suggesting that either hyperons don't appear, or if they do, their effects are offset by other forces we don't yet understand. Similarly, ideas about Kaon condensates or free quark matter face tight constraints from these massive survivors. Some people even wonder if neutron stars that are heavier than 2.5 solar masses might exist. It would be hard to tell the difference between neutron stars and black holes if they did that. The largest neutron stars that have been found so far are just above 2 solar masses, but the search is still going on. Gravitational wave data have shown that some small objects seem to be in the mass gap, which is the space between the largest known neutron stars and the smallest black holes. It would change the way we think about dense matter if any of those turned out to be neutron stars. The cooling problem. When they're first formed, neutron stars are some of the hottest things in the universe. As soon as a supernova goes off, their surfaces can glow with millions of degrees of heat, and the insides are even hotter. Over time, they give off energy, mostly in the form of X-rays and neutrinos, which are ghost-like particles that can move through matter almost without interacting with it. When scientists try to figure out how fast neutron stars cool, they find that some stars cool off much faster than expected, while others stay warmer for a much longer time. One of the clearest signs that something very strange is going on inside their guts is that they are having trouble slowing down. The basic theory of neutron star cooling says that neutrino emission should dominate in the early stages. As the star gets older, photon emission from the surface takes over. If the core is made mostly of neutrons, protons, and electrons, this process should follow a fairly predictable curve. But real observations don't line up neatly with that curve. Some young neutron stars have cooled surprisingly quickly, while others seem to hold their heat. The differences suggest that exotic forms of matter or unexpected processes are at work deep inside. One famous example is the neutron star in Cassiopeia A, a supernova remnant about 11,000 light-years away. When scientists used NASA's Chandra X-ray Observatory to track its temperature, they saw something shocking. Over just a decade, the star's surface temperature dropped by about 4%. That's much faster cooling than models predicted. The leading explanation is that the neutrons in the core formed a superfluid, a strange quantum state that allows them to pair up and move without resistance. When this transition happens, it releases a burst of neutrinos, accelerating the cooling process. Other neutron stars show the opposite behavior. They appear warmer than expected, even at ages where models say they should have cooled dramatically. This suggests that something inside is acting like a heater, injecting extra energy into the star. One possibility is that strong magnetic fields, like those in magnetars, twist and crack the crust, releasing heat. Another idea is that exotic particles in the core, like kaons or quarks, might change the way neutrinos escape, slowing down the cooling process. The cooling problem ties directly into the question of what the star's equation of state really is. Different phases of matter, neutrons, hyperons, mesons, or quarks, all change how neutrinos are produced and how heat flows. For example, if hyperons exist in the core, they could allow rapid neutrino processes that bleed energy away faster, cooling the star more quickly. On the other hand, if quark matter forms, it might suppress certain cooling channels, keeping the star warmer for longer. Each possibility leaves a distinct fingerprint in the cooling curve, but so far, no single model explains all observations. Cooling is also influenced by what happens in the crust. The outer layers of a neutron star can insulate the interior, slowing heat loss. If the crust has unusual composition, such as nuclear pasta structures, it could trap or release heat differently. The presence of superfluid gaps, or superconducting protons in the outer core, can also alter how neutrinos are produced. This makes cooling a kind of indirect diagnostic tool. By comparing real neutron star cooling with theoretical models, scientists can infer what exotic states might exist inside. A very interesting finding is that some neutron stars may occasionally heat up again. When this happens, the star cools down regularly for a while, and then all of a sudden starts to warm up again. This might happen because of star quakes, which stress the shell and cause it to crack, or because of problems with the spin that move the star's superfluid inside around. When this happens, energy that was stored in the star's structure is released as heat, which temporarily stops the cooling trend. Future X-ray telescopes, like the planned Athena mission in Europe, will also give sharper looks at neutron star cooling. By observing larger samples of stars at different ages, scientists can map out the cooling curve more precisely. Right now, the number of neutron stars with detailed temperature histories is small, so each new measurement has an outsized impact on theory. Expanding that sample will help separate universal cooling patterns from individual quirks caused by magnetic fields or accretion. The symmetry energy mystery. The most basic but tricky idea in nuclear physics is symmetry energy. This is where you start to understand why neutron stars are so hard to understand. Even though it seems vague at first, symmetry energy is a key part of working out what goes on inside the core of a neutron star. In simple words, it checks how much extra energy is needed when matter changes from having the same number of protons and neutrons to having different amounts. Most stable elements have about the same number of protons and neutrons, so atomic nuclei on Earth are pretty close to being balanced. That balance is broken inside a neutron star, though. The huge ball of matter you see is mostly made up of neutrons, with some protons and electrons thrown in for good measure. That means symmetry energy is very important, but experts still don't know how it acts in these very harsh situations. In laboratory experiments, we can study symmetry energy by smashing heavy ions together at near light speeds. These collisions briefly create matter with more neutrons than protons, mimicking in a tiny way the imbalance inside a neutron star. From these experiments, scientists can get hints about how symmetry energy behaves at densities close to normal atomic nuclei, but neutron stars push matter way beyond that, up to several times nuclear density. At those levels, experiments on Earth can't reproduce the conditions, leaving a huge gap in our understanding. Why does symmetry energy matter so much? Because it directly affects how dense matter pushes back against gravity. If the symmetry energy grows rapidly at high density, it makes matter stiffer, allowing neutron stars to support more mass without collapsing. If the symmetry energy softens, matter becomes squishier, and neutron stars can't get as heavy. This means that the true form of symmetry energy is tied to the maximum mass of neutron stars, a crucial number that astronomers are still trying to pin down. Symmetry energy also controls the proton fraction inside neutron stars. Even though they're mostly neutrons, there are always some protons present, and those protons play a big role in processes like neutrino emission. If symmetry energy favors fewer protons, the star may cool slowly. If it allows more protons, rapid neutrino emission channels open up, and the star cools faster. This makes symmetry energy a hidden player in the cooling problem we just explored. It's not just about density, it's about balance between particles. The problem is that we can pretty accurately measure symmetry energy at nuclear levels right now. But when we go to the core of a neutron star, where the pressures are very high, the error goes through the roof. The answers depend on the type of nuclear model used. Some people think that there will be stiff matter that can easily hold two solar mass stars. Others think there is softer matter that should fall apart. But those ideas don't match up with the heavy neutron star oddities that scientists have already found. Because theory and reality are at odds with each other, symmetry energy is one of the most controversial ideas in astronomy right now. Putting together data from the lab and views from space is one way to solve the problem. For example, studies at particle reactors like RHIC in the US or FAIR in Germany are meant to find out how far neutron-rich matter can go. At the same time, NICE's readings of neutron star radii and its discovery of gravity waves from star mergers give us real-world information from space. The goal of science is to find the true form of symmetry energy by putting these two very different types of data together. The symmetry energy mystery doesn't just affect neutron stars, it has implications for the entire cosmos. For example, it influences how elements are created in neutron star mergers. If symmetry energy favors more protons, that changes the balance of reactions during the merger, affecting the abundance of heavy elements like gold and platinum that are forged in those events. In this way, understanding symmetry energy is connected not only to the structure of stars, but also to the origin of matter on Earth. There are even theories that say symmetry energy might hide hints about completely new states of matter. If quarks are free at high densities, symmetry energy could act in strange ways, like suddenly becoming flat or changing its slope. This kind of action could be a sign of a phase change deep inside the star that can't be seen in the lab. If that's true, neutron stars might be the only places in nature where this kind of physics can be tried. The solid versus liquid debate. Neutron stars are often thought of as huge, incredibly dense balls of neutrons that are so packed together that nothing can move. The truth is much stranger though. Scientists are still not sure if a neutron star's deepest core is more like a solid crystal or a liquid ocean of strange particles. People argue about whether something is solid or liquid. This is one of the main secrets about what's inside these stars. At first glance, it might sound simple. On Earth, we're used to matter existing in familiar states, solids with fixed shapes, liquids that flow, gases that expand, and plasmas that glow. But neutron stars don't play by the same rules. Their densities reach billions of tons per teaspoon. At these extremes, the forces between particles behave in ways that can't be recreated in any lab on Earth. As a result, the matter inside may blur the line between solid and liquid, or switch between them depending on depth. We know the outer crust of a neutron star is solid. It's made of a lattice of nuclei, mostly iron-like or heavier elements, suspended in a sea of electrons. This outer crust is rigid and can crack, which is why we sometimes observe star quakes. But deeper down, where pressures rise, atomic nuclei dissolve into individual neutrons and protons. At that point, the material may act like a liquid, though one with properties utterly unlike water or molten rock. The inner core is where the real debate begins. Some physicists argue it could form a solid lattice of exotic particles, such as quark clusters or strange matter. If that's true, the star's heart might be crystalline, with enormous rigidity compared to anything known. Others suggest it's a superfluid liquid, where neutrons pair up and flow without resistance, filling the core with a ghost-like quantum ocean. Both ideas have evidence in their favor, but neither fully explains all the observations. Computer models show that under extreme pressure, matter could organize itself into phases more complex than anything on Earth. Some predict quark crystals, solid lattices of quark matter that could form a rigid core. Others show that superfluid neutrons and superconducting protons could coexist in layers, creating a hybrid interior with both fluid-like and solid-like behaviors. These models suggest that the reality might not be an either-or situation, but a bizarre mix of states that we don't yet have words for. Cooling observations add one more twist. Neutrinos are made and exit more or less quickly, depending on how much superfluid matter is inside neutron stars. As seen in stars like Cassiopeia A, this would change how fast it cools down. Though if the heart were solid, the cooling would happen in a different way. Comparing cooling trends to models hasn't ended the argument, but it strongly suggests that the behavior of superfluids is very important. The magnetic fields of magnetars may also offer clues. These stars have magnetic fields trillions of times stronger than Earth's. To sustain that level of stress, the interior must have some solid-like rigidity. Otherwise, the field would twist and rearrange too quickly. This points to at least part of the core having solid properties, even if much of it behaves like a fluid. Heavy ion impacts in the lab give us very little information about what happens at very high densities, but they only last a few hundredths of a second. Neutron stars have been giving us nature tests for millions of years. Every glitch, quake, and cooling event tells us something about whether the matter inside is more like a solid or a liquid. Still, experts can't do a direct probe, so they have to put together pieces of data from far away. The solid versus liquid debate isn't just about classification. It shapes how neutron stars evolve. If the core is solid, starquakes could be more violent, releasing bursts of energy we see as X-ray or gamma-ray flares. If it's liquid, internal flows could redistribute momentum, causing subtle changes in spin. Each possibility predicts different astrophysical behaviors, which astronomers are trying to match to real observations. The speed of spin limits. Neutron stars are famous for spinning at incredible speeds. Some rotate dozens of times per second, others hundreds. The fastest known neutron star spins over 700 times per second. So fast that a spot on its equator is moving at nearly a quarter the speed of light. But this incredible speed raises a big question. What's the ultimate limit? How fast can a neutron star really spin before it tears itself apart? The answer should seem straightforward. Just balance gravity pulling inward against centrifugal force pulling outward. But in reality, the spin limit mystery has proven far harder to solve, and it has exposed gaps in our understanding of what's inside these stars. The first issue is structure. Neutron stars are not rigid balls. Their outer crust may act like a solid, but deeper inside, superfluid neutrons and superconducting protons change how the star responds to rotation. If the core behaves more like a liquid, it can redistribute momentum differently than a solid would. This makes the exact calculation of maximum spin rate very uncertain, because the physics of the interior is still unknown. Theoretical models predict a breakup speed, the fastest a neutron star could spin before its outer layers fly off. Depending on the assumed equation of state, this speed should be around 1,000 to 1,500 rotations per second. Yet despite years of searching, astronomers have never found a neutron star spinning anywhere near that fast. The fastest remain below 800 per second. Why? That's the puzzle. Either something is stopping stars from reaching the predicted limit, or our models of the equation of state are wrong. Gravitational waves slowing down could be one reason. When a neutron star spins very quickly, tiny flaws in its shape, like mountains that are only a few centimeters high, can send out gravity waves. There is no way for stars to ever reach very high speeds, because these waves take away their angular momentum. If this is true, Then gravitational waves are quietly telling the fastest pulsars how fast they can go. LIGO and Virgo may finally pick up on these weak signals, which would be direct proof. Magnetic stopping is another way to explain it. Neutron stars are magnetic dynamos, and their fields pull on the plasma around them as they spin. Over time, this process slows them down. If the magnetic fields are strong enough, they might stop stars from ever speeding up to the potential top speed. This might explain why pulsars that are just a few thousand years old start spinning more slowly after supernova blasts. Accreting neutron stars, those that pull matter from a companion star, add another twist. As matter falls onto the neutron star, it transfers angular momentum, spinning the star up. This process should, in theory, push some stars close to the breakup speed. Yet even in these systems, the spin seems to stall out below the predicted maximum. Something must be bleeding away angular momentum just as quickly as it's being added. Again, gravitational waves are a prime suspect, though superfluid dynamics inside the star may also play a role. The superfluid interior complicates things further. Superfluids rotate by forming quantized vortices, tiny whirlpools that carry angular momentum. These vortices can pin to the crust and then suddenly unpin, leading to the glitches astronomers observe. If the interior's vortex network resists rapid spin-up, that could impose a hidden speed limit. In this view, the star's quantum interior acts like a safety valve, preventing it from spinning too fast. Spin limits also intersect with the question of maximum neutron star mass. The faster a star spins, the more centrifugal support it gains against gravity, meaning it can be more massive before collapsing into a black hole. If we could find a neutron star spinning near the true limit, it would reveal the maximum stable mass. The fact that we haven't may mean nature enforces a strict barrier that keeps stars away from this critical regime. R-mode problems are another idea. These are ripples that can get stronger inside neutron stars that spin very quickly. They are caused by gravity waves. If R-modes become unstable, they might take away the star's energy and rotational momentum, which would stop it from spinning faster. You could say that the star's own fluid movements could limit how fast it can turn. Collapse threshold unknowns. Neutron stars are right on the edge of surviving and collapsing. They are already squished so badly that the strange forces of nuclear matter barely hold them back. If you push them just a little bit further, they will cross an imaginary line and fall into a black hole. The collapse threshold line is one of the biggest riddles in astrophysics that hasn't been answered yet. We know it's there, but we don't know where it is or why some stars seem to go against it. The collapse threshold is the maximum mass and density that a neutron star can reach before gravity wins. Below that limit, the pressure of neutrons, superfluids, and possible exotic particles inside is enough to keep the star from shrinking further. Cross it, and no known force can stop the implosion. The star's core vanishes into a black hole, leaving only its event horizon behind. The big problem: scientists can't agree on the exact value of this maximum. We don't know the equation of state of ultra-dense matter, which shows how pressure and density inside relate to each other. Neutron stars can hold more mass if the equation is stiff. They fall down faster if it's soft. Different ideas about what goes on inside the core, like hyperons, quark matter, and strange condensates, lead to very different conclusions. As few as 2.1 solar masses, or as many as 2.9, could cause the system to break apart. That's a very large range for astronomy, and it's hard to tell which stars should still be around, and which ones should have already turned into black holes. Rotation makes things even more difficult. Because centrifugal force helps against gravity, a neutron star that spins can hold more mass than one that is not moving. This means the point at which things start to fall apart is not a fixed number, but changes based on spin. A neutron star that spins very quickly might stay stable at 2.6 solar masses, but one that doesn't spin would fall apart at 2.2. As time goes on and the star spins less fast, it could lose that support and fall apart without notice. Astronomers have even said that some strange gamma-ray bursts might be the last warning signs of these kinds of delayed crashes. Magnetic fields also add to the confusion. In magnetars, Fields are so strong that they may alter pressure inside the star. If fields can stiffen matter, they could allow slightly higher maximum masses. On the other hand, if fields add stress in unstable ways, they might lower the collapse point instead. Right now, no one is sure which effect dominates. Another complication is the possible existence of twin stars, stars of the same mass but with different internal structures. In this scenario, one configuration might be stable, while another collapses. That would mean the collapse threshold is not a sharp line, but more like a branching decision, where one star lives and another dies even at the same mass. This idea ties into the possibility of exotic matter like quarks or hyperons suddenly appearing inside, flipping the stability conditions. Astronomers also don't understand what temperature has to do with it. Neutron stars that were just made from supernova explosions are very hot, with core temperatures that can hit hundreds of billions of degrees. Because heat changes the pressure inside, the star might be able to hold more mass for a short time. That backing will weaken as it cools though, and it could fall apart after that. So the collapse barrier doesn't stay the same, it changes as the star grows. The origin of starquakes. Quakes happen on Earth when tectonic plates move and release stress that has been building up. Neutron stars have something similar happen, but it's a lot worse. Starquakes are these kinds of events, and they release more energy in a very short amount of time than our world does in decades of earthquakes. Figuring out where they come from is now one of the most interesting and confusing ways to look into the strange physics inside neutron stars. The first hints of starquakes came from observations of pulsars. Neutron stars that beam regular pulses of radio waves as they spin. Astronomers noticed that some pulsars suddenly changed their spin rate by tiny but measurable amounts. These changes, called glitches, happen too quickly to be caused by outside forces. Something inside the star must be snapping or shifting. That something is the star's crust. The crust of a neutron star is an iron-hard lattice of nuclei floating in a sea of electrons. It's only a few kilometers thick, but it carries incredible stresses. As the star cools, spins, and interacts with its magnetic field, pressure builds in this crust. Eventually, the strain grows too much, and the crust cracks or shifts suddenly, releasing energy in a quake. These starquakes send shockwaves rippling through the star, and in magnetars, they can even trigger bursts of gamma rays detectable across the galaxy. But the story doesn't stop at the crust. Inside the star lies a quantum superfluid of neutrons. This strange material can flow without friction, but it rotates differently than a solid crust does. The superfluid stores angular momentum in quantized vortices, like tiny tornadoes. These vortices can pin to the crust. As the crust spins down over time, the pinned vortices resist change, creating a mismatch between the inner superfluid and the outer shell. Eventually, the vortices break free, transferring angular momentum in a sudden jump. This is believed to be a key cause of pulsar glitches, linking starquakes to the quantum mechanics of the core. The magnetic fields in magnetars are so strong that they bend the crust of the star. Over time, this stress builds up like a spring being wound up. When the crust finally breaks, the energy that is released can cause huge flares. These are bursts of energy that are so strong that they have been caught by satellites circling Earth from magnetars thousands of light years away. This is why these bursts happen in rapid, unpredictable jumps instead of as steady emissions. The starquake model. Starquakes don't just shake the crust, they may also rearrange the magnetic field itself. When the crust cracks, magnetic lines of force anchored to it can snap or reconnect, unleashing even more energy. Some astronomers compare it to solar flares on the Sun, except multiplied by billions. This process could explain why magnetar bursts often have both seismic-like signatures and sudden electromagnetic fireworks. The detection of quasi-periodic oscillations, QPOs, in magnetar flares has added weight to the starquake idea. These are subtle vibrations in the X-ray light that follow giant bursts, almost like aftershocks. They are thought to be caused by the neutron star ringing like a bell after its crust shifts. By studying these oscillations, scientists can estimate the stiffness of the crust, and the depth of the cracking, turning star quakes into natural laboratories for extreme physics. The big mystery, however, is exactly how deep these quakes go. Some models suggest they are confined to the outer crust, where stresses are easier to build. Others argue they extend into the inner crust or even affect the boundary with the core, involving pinned superfluids. If deeper regions are involved, it means starquakes could provide rare evidence of exotic states of matter inside, something no other observation can easily reveal. On a human level, it's hard to picture how bad a starquake would be. The rock might only move a few centimeters during a normal earthquake. But when you're working with a sphere 20 kilometers across and as heavy as 2 suns, that tiny change releases an enormous amount of energy. Some bursts caused by starquakes have briefly been brighter than all the stars in our galaxy put together. The hidden particle zoo. A lot of people say that neutron stars are like big atomic cores, but that's not the whole story. Matter is so squished deep inside their guts that known particles may break apart or change into completely different ones. This is what scientists call the thought of a hidden particle zoo, a gathering of strange particles that may only be found in the cores of neutron stars and have never been seen in a lab on Earth. To understand why, think about the pressures involved. A neutron star crams more than a sun's worth of mass into a ball only 20 kilometers across. The density is so high that a teaspoon of neutron star material would weigh billions of tons. Under these conditions, normal protons and neutrons are squeezed to their limits. Eventually, the rules of quantum mechanics and nuclear forces suggest that other, stranger particles may appear. The Hyperon is a possible possibility. It is related to the neutron and has more than 2 weird quarks, not just up and down quarks. Hyperons have been seen in particle reactors on Earth, but they are unstable and break down quickly when things are normal. But in a neutron star, the very high pressure might keep them stable. The trouble is that hyperons weaken the equation of state, which means they lower the pressure that keeps things from falling apart. If there are too many hyperons, the star should fall apart into a black hole with a mass much smaller than what we see. Still, neutron stars with masses greater than 2 solar masses are known to exist. There is a conflict that we call the Hyperon puzzle. It means that either our understanding of hyperons is incomplete, or there is another force inside them that cancels them out. Kaon condensates are another unusual choice. A quark and an antiquark are what mesons are made of. Theories say that kaons might combine into a single quantum state at very high numbers, creating something similar to a Bose-Einstein condensate. This would greatly change how matter acts inside if it happens. It could also speed up cooling by making neutrinos come out faster. Again though, the proof from observations isn't very clear, and kaons are still just a guess. The most radical suggestion is that neutrons themselves may dissolve into their constituent quarks, forming quark matter. If that's true, then entire cores of neutron stars might be filled with free quarks, behaving like a dense soup. Even more extreme is the idea of strange quark matter, which mixes up, down, and strange quarks in a stable blend. Some scientists argue this state could be more stable than ordinary nuclear matter, meaning that once formed, it might not decay back. If so, then some neutron stars could actually be strange stars, built mostly out of quark matter rather than neutrons, and the zoo might not stop there. Theorists have even proposed dark matter particles could collect inside neutron stars. If dark matter interacts, even weakly, with ordinary matter, neutron stars could capture it as they orbit through the galaxy. Over billions of years, the buildup could change their structure, altering spin rates, cooling behavior, or even collapse thresholds. Detecting unusual signals from neutron stars might someday hint at the fingerprints of dark matter hiding inside. Other speculative particles include axions, hypothetical lightweight particles originally proposed to solve problems in quantum theory. If they exist, neutron stars could produce them in large quantities. Likewise, sterile neutrinos, a possible form of neutrino that barely interacts with anything, might influence cooling rates if they escape from the dense core. None of these particles have been confirmed, but neutron stars remain one of the best laboratories in the universe to test for them indirectly. The trouble is that we can't look inside directly. Neutron stars are studied by watching how they act, like how fast they spin, how fast they cool, how heavy they can get before they fall apart, and how they shake space-time when they hit each other. Each discovery gives hints about the particles that might be at work inside. For instance, if stars cool down faster than expected, it could mean that strange condensates are making neutrinos come out more. If stars can get heavier than expected, quark matter may help them stay in place. If sudden glitches happen, pinned swirls in superfluid matter might show us new forces inside the universe. Each of these particles, hypons, kaons, pions, quarks, axions, and possible dark matter, could exist at the same time, which is very interesting. At different depths, different types of neutron stars might be dominant. The core of a neutron star could be stacked or mixed. Hyperons could be found in one area, quark soup in another, and meson condensates in a third. It might not be so much a simple structure as an environment of strange matter that is always balancing forces that we don't fully understand. Heavy ion collisions on Earth. Neutron star cores are places with unbelievably high pressure, where matter is squished so tightly that we can't even make it again. Scientists have to think of other ways to study neutron stars since we can't go there or take a sample of their core. The heavy ion impact experiment is one of the most useful tools they have. Scientists are trying to make tiny flashes that look like the very harsh conditions inside neutron stars by smashing big atomic nuclei together at almost the speed of light. Even though these tests only last a few hundredths of a second, they tell us a lot about what happens when all the limits of matter are reached. The idea is simple on paper, but mind-boggling in practice. Take a nucleus of a heavy atom, like gold or lead, and accelerate it to a speed close to light. Do the same with another nucleus, then collide them head-on. In that instant, the protons and neutrons inside the nuclei slam into each other so violently that they break apart, creating a fireball of quarks, gluons, and exotic particles. For a split second, the collision recreates a state of matter that scientists think resembles conditions in the cores of neutron stars, or even the first microseconds after the Big Bang. These experiments are done in particle colliders like the Large Hadron Collider, LHC, in Switzerland, and the Relativistic Heavy Ion Collider, RHIC, in the United States. At RHIC, gold ions are accelerated until each nucleus carries energy equivalent to hundreds of times its own mass. At the LHC, lead nuclei collide with energy so intense they briefly form what's called a quark-gluon plasma, a state where quarks and gluons, normally locked inside protons and neutrons, are free to move around. Why does this matter for neutron stars? Because one of the big questions about neutron star cores is whether neutrons remain intact or dissolve into quark matter under extreme pressure. Heavy ion collisions give scientists a way to study how matter transitions from one phase to another. By analyzing the debris from these collisions, the spray of new particles and radiation, researchers can piece together the properties of matter at densities and temperatures similar to those expected in neutron star interiors. The LHC and RHIC have made some interesting discoveries. One is that quark-gluon plasma doesn't behave like a chaotic gas, but more like a perfect fluid, moving with almost no resistance. This came as a surprise, and it fits with ideas that neutron stars contain superfluids, which are forms of matter that also move without friction. There isn't an exact link between the two, because colliders make matter that is very hot, while neutron star cores are very thick and cool. But they both involve matter in ways that regular nuclear physics doesn't work. So what we learn from one helps us improve our models of the other. Heavy ion collisions also help address the question of symmetry energy, how the balance of neutrons and protons affects the behavior of nuclear matter. Neutron stars are mostly neutrons, with only a small fraction of protons and electrons mixed in. On Earth, it's hard to recreate systems with such extreme neutron dominance. But heavy ion experiments allow scientists to tweak the neutron to proton ratio of the colliding nuclei, testing how matter responds. These results can then be compared with neutron star observations, like how fast stars cool or how massive they can become. Another critical point is pressure. By analyzing the particle flow patterns from collisions, researchers can estimate how much pressure builds up inside nuclear matter at different densities. This feeds directly into the elusive equation of state, the relationship between density and pressure that determines whether a neutron star survives or collapses into a black hole. Without heavy ion collisions, we'd have almost no experimental data to guide these models. Of course, there are limits. Neutron stars are incredibly cold compared to the fireballs in colliders. A neutron star's core may reach around 1 trillion degrees at birth but cools quickly, while the quark gluon plasma at the LHC is much hotter, albeit fleeting. This means the conditions aren't identical. Still, the extreme densities and pressures achieved in these experiments provide valuable analogies. Even if we can't duplicate a neutron star, we can at least probe some of the physics that governs its insides. Heavy ion collisions have also revealed hints of new states of matter. In some experiments, researchers have detected unexpected particle correlations or flow patterns that suggest exotic physics is at play. These could be linked to the same kinds of strange matter phases, like hyperons, Kaon condensates, or quark soups, that might exist in neutron star cores. While no direct proof exists yet, the parallels keep theorists busy, adjusting their neutron star models to match both collider results and astrophysical observations. The proton fraction problem. At first look, the name neutron star makes it sound like these things are made of neutrons only. It's not that easy in real life. Plenty of protons and electrons can be found in even the densest stars in the universe. The amount of them is very important. This balance is called the proton fraction, and it shows how many protons there are compared to neutrons inside the star. One of the most important problems in astronomy is figuring out this fraction. It affects everything, from how neutron stars cool down to whether they turn into black holes. The story begins with the basic building blocks of matter. A normal atom has protons and neutrons in its nucleus, with electrons orbiting around. In a neutron star, gravity crushes matter so tightly that electrons are forced to merge with protons, creating more neutrons. This is why neutrons dominate. But not all protons are swallowed up. Some survive, and the percentage that remains plays a huge role in the star's behavior. There is a process called the straight-Urker process that makes the proton fraction important. The neutrinos it sends out are a very strong way for it to lose heat. There need to be enough protons in the core for this process to work well. The straight-Urker process starts when the proton fraction is above a certain level, which is about 11 to 15%. This makes the star cool down much faster than predicted. If it's lower, the star cools more slowly, and weaker neutrino processes take over. Neutron stars cool down at different rates. Some cool down surprisingly quickly, while others cool down much more slowly. The different types of stars show that the proton fraction is not the same, which brings up a lot of important questions about what controls it. The proton fraction also affects how stiff or soft the star's matter is. Neutrons repel each other in dense conditions, but protons, with their electric charge, add a different kind of interaction. The ratio between them influences the symmetry energy, a property that tells us how much energy it costs to have unequal numbers of protons and neutrons. Unfortunately, symmetry energy is one of the least well understood aspects of nuclear physics. Laboratory experiments can probe it by smashing heavy ions together, but they can't reach the exact densities found inside neutron stars. This uncertainty leaves scientists unsure about whether neutron star matter resists compression strongly or weakly, which in turn affects the maximum mass a neutron star can have. Superfluidity and superconductivity inside the star are additional explanations why the proton fraction is important. Neutrons can pair up to make a superfluid that doesn't have any friction, and protons can pair up to make a superconducting state. But the number of protons present has a big effect on the features of these quantum stages. If there are too few protons, superconductivity might go away. If there are too many, the balance of forces changes in ways that are hard to predict. This might be the reason why the spin of some pulsars changes quickly and others stay steady for long periods of time. Astronomers try to measure the proton fraction indirectly by observing neutron stars. Cooling rates are one clue. Another comes from gravitational waves during neutron-star mergers. The way two stars deform before colliding depends on their internal pressure, which in turn depends on the proton fraction. NASA's X-ray mission on the International Space Station also contributes by mapping the size and shape of pulsars, providing constraints on the equation of state that governs neutron-proton balance. Theoretical models complicate things further. Some predict that as density rises, protons may actually vanish almost completely, leaving pure neutron matter. Others suggest the opposite, that exotic processes could increase the number of protons by creating strange particles or quark matter. If quarks break free inside, the distinction between proton and neutron may not even apply anymore. In that case, the whole concept of proton fraction might need to be redefined. On Earth, tests have been done to try to narrow down the options. Physicists can test how nuclear matter acts with different amounts of neutrons and protons by crashing heavy ions into each other. They hope to find the symmetry energy, and by extension, the proton fraction by matching the results with readings made in space. But as of now, there isn't a single model that fits all the data on cooling, mass boundaries, spin behavior, and gravity wave results. Because of this difference, the proton fraction is still one of the most difficult problems in neutron star physics. The proton fraction problem even touches on black hole formation. The critical threshold that separates a neutron star from collapsing into a black hole depends on how matter balances itself at extreme densities. If protons contribute more pressure support than expected, stars might survive longer before collapsing. If they contribute less, stars might tip into black holes more easily. In this way, the unseen fraction of protons inside can literally determine whether a star remains visible in the universe or disappears forever behind an event horizon. The enigma of exotic pressure. Most of the time, when we think of pressure, we picture air pressing against our skin or the force of water pushing us back up as we dive deep into a pool. But inside a neutron star, the idea of pressure changes into something completely different. The strange pressure in these stars isn't caused by water or air. It might be caused by quantum mechanics, nuclear forces, or even new types of physics that don't exist anywhere else. It is very important to understand this pressure because it determines whether a neutron star stays steady, falls apart into a black hole, or changes into something else. Scientists have studied this for decades, but they still can't figure out what gives the huge internal support. On Earth, pressure is caused by particles moving around and colliding with one another. Inside a neutron star, most of the matter is locked into neutrons crammed together so tightly that their quantum nature takes over. Neutrons, like protons and electrons, are fermions, particles that obey the Pauli exclusion principle, which says no two identical fermions can occupy the same state. This rule creates what's called degeneracy pressure, a kind of pushback that resists further compression. Degeneracy pressure is already strong enough to hold up white dwarfs against gravity. But in neutron stars, gravity is so extreme that degeneracy pressure alone isn't enough. Something more must be happening. That something more is nuclear force. The strong interaction that binds quarks into protons and neutrons, and those protons and neutrons into atomic nuclei. When neutrons are packed as tightly as they are in a neutron star, the strong force begins to dominate. It can be repulsive at very short ranges, giving neutrons extra pressure against collapsing further. But how exactly this balance works under such intense conditions is still not clear, because we cannot recreate neutron star densities in any lab on Earth. The equation of state, the mathematical relationship between pressure and density, is supposed to describe what happens inside neutron stars. But observations don't line up neatly with any single equation. Some neutron stars appear to have very stiff matter, resisting compression strongly and allowing them to reach high masses without collapsing. Others seem softer, with matter that compresses more easily. This suggests that exotic forms of pressure may appear at different depths, perhaps switching between different states as density increases. It's possible that strange particles like quark matter, hyperons, or Kaon condensates could show up in the core and change the balance of forces. When hyperons are present, they can cause new reactions that can lower the pressure, which increases the chance of collapse. If quarks interact in the right way, quark matter might make things stiffen up again. Because of these additions, the pressure inside the core might not be smooth and even. Instead, it might change quickly, like there are different materials stacked on top of each other inside. One peculiar thing about neutron star pressure is that it doesn't always act like normal pressure. In some models, pressure doesn't rise evenly as density does. Instead, it can stop rising or even drop quickly when new phases of matter show up. This is known as a phase shift, which is like how water can quickly turn into ice or steam when the conditions are right. If the heart of a neutron star goes through this kind of change, its pressure profile could suddenly change. This could lead to what some scientists call twin stars, which are neutron stars with the same mass but different sizes and internal structures. The Enigma also extends to stability limits. A neutron star must generate enough internal pressure to balance the crushing weight of gravity. If the pressure comes up short, the star collapses into a black hole. But observations of neutron stars heavier than 2 solar masses tell us that nature somehow provides enough pressure to keep them intact. Our current models struggle to explain this. If hyperons or kaons appear, pressure should drop and stars should collapse earlier than observed. If quark matter appears, it might help, or it might not, depending on unknown details of quark interactions. Some experts think that dark matter might even play a part. Dark matter particles stuck inside neutron stars could change how pressure builds up. It's possible that these particles could either make the star less resistant to falling apart, or, strangely enough, make it stronger. It's just a guess, but it shows how broad the search for answers has become. Heavy ion crashes in the lab give us information about unusual pressure. Scientists can make short states of matter that look like the insides of neutron stars by smashing heavy nuclei together at speeds close to the speed of light. Researchers can test different models of pressure by looking at how particles move and how energy is distributed during these clashes. But once more, the tests only get to a small part of neutron stars' real density, which means that a lot of the puzzle is still unsolved. The preon hypothesis. It was thought by experts for many years that protons and neutrons were the smallest building blocks of matter. Then there were quarks, which are even smaller particles that make up neutrons and protons. The standard model of particle physics, which gives us the best picture of how matter is put together, is based on quarks and leptons like the electron. What if, though, quarks aren't the bottom layer? What if they're made of something even smaller? This is the big idea behind the preon theory, which says there might be subparticles that are even more basic than quarks. If that's true, the neutron stars' hearts might be the best place to find them. The word preon comes from pre, meaning before, and on, a suffix used for particles. Preons are purely hypothetical. No experiment has ever seen one. But some scientists propose them because the standard model, while successful, feels incomplete. For one thing, quarks and leptons come in multiple flavors and generations, but no one knows why. Why should nature need 6 types of quarks and 3 types of neutrinos, each with wildly different masses? A simpler explanation could be that these particles are actually composites of something more basic, preons. So how does this connect to neutron stars? Neutron stars crush matter to densities far beyond what we can achieve in laboratories. In such extreme conditions, quarks themselves may no longer stay confined inside neutrons and protons. If quarks are truly fundamental, they'd simply roam free in what scientists call quark matter. But if quarks are made of preons, then under such crushing density, the deeper layer of preon structure might emerge. In other words, Neutron stars could be preon laboratories hidden in the cosmos. If preons exist, their presence would radically change how matter behaves at ultra-high densities. Instead of a quark-gluon soup, the star's core might dissolve into a preon plasma, an even stranger state of matter where particles smaller than quarks determine the rules. Such a plasma might generate pressure differently, altering the equation of state that describes the star's balance against gravity. This could explain why some neutron stars seem unusually massive. Perhaps preon matter provides extra resistance to collapse. Preon stars are exciting ideas that could come from the preon idea. These are small stars that are even denser than neutron stars, but not quite black holes. A preon star would have a radius much smaller than any known neutron star, but it would have a huge amount of mass. Some scientists think that preon stars might be out there in the world right now, hiding as black holes or other small things. If it's true, it would mean that we've been calling some of the most distant things in the universe by the wrong names. But how could we ever tell if preons are real? One way might be through gravitational waves. When neutron stars merge, their internal structure affects the signal we detect on Earth. If preon matter behaves differently from quark matter, it could leave a distinct fingerprint in the wave pattern. Another way could be through neutron star cooling. Preons might allow entirely new channels for neutrino emission, changing how quickly stars lose heat. If some neutron stars cool faster or slower than quark models predict, preons might be the missing ingredient. Laboratory experiments also try to test the preon idea, though they face limits. Particle accelerators like the Large Hadron Collider smash protons together at incredible energies, probing quarks in search of smaller substructures. So far, quarks still appear point-like. No evidence of preons has shown up. But neutron stars reach densities far beyond collider experiments. This is why astronomers keep them in mind as potential testing grounds for physics beyond the standard model. Thoughts have also been put forward about how preon matter might act. Some ideas say it could turn into a fluid that is almost impossible to squeeze. This would make stars very stiff and able to hold more mass than expected. Others say it could lead to strange superconductivity, or even completely new types of pressure that aren't known to exist in nuclear or quark physics. Any of these results would have a huge impact on how neutron stars spin, cool, and finally die. Of course, many physicists remain skeptical of preons. Without experimental evidence, the idea is still highly speculative. The standard model has been tested to incredible precision, and so far, quarks look fundamental. If preons exist, they must be incredibly small, beyond even our most powerful colliders. But science often advances by questioning whether the final answer is really final. Just as quarks once replaced protons and neutrons as the basic building blocks, preons may one day replace quarks. Why no consensus exists. We have looked at, calculated, and done tests for decades, but we still can't agree on what is really inside the core of a neutron star. It's not that scientists aren't trying. It's just that neutron stars push the limits of physics so far that our best ideas and facts are always running into each other. The answers get weirder as we dig deeper, and each new finding makes things even less certain. The first reason for the lack of consensus is that neutron stars are inaccessible. We can't send a probe into one. We can't scoop up a sample from the core. Everything we know comes from indirect measurements: X-rays, radio waves, gravitational waves, cooling curves, and spin rates. These observations give us hints, but never a complete picture. For every piece of evidence pointing one way, another set of data seems to point in the opposite direction. Take the equation of state, the relationship between pressure and density inside the star. Some models suggest neutron star matter is extremely stiff, able to resist collapse and support stars weighing more than 2 solar masses. Other models say it's soft, compressing more easily. Observations confirm both possibilities, depending on which neutron star you look at. The fact that different stars seem to follow different rules suggests that no single description fits all of them. The second reason is that multiple exotic states of matter might exist at once. Some theories predict hyperons in the core, others Kaon condensates, others quark matter, and still others Pion or even preon states. Each exotic particle or phase changes the star's internal pressure in a unique way, but we have no direct proof of any of them. Instead, scientists build models that include these possibilities, only to find contradictions when compared with real neutron star data. It's like trying to solve a puzzle where the pieces change shape every time you look at them. The third reason is that different tools give different answers. Gravitational waves from neutron star mergers tell us how squishy or stiff stars are before collision. NICE's X-ray mapping gives us estimates of radius and surface hotspots. Cooling observations show how fast some stars lose heat. But when all these methods are compared, they don't match neatly. For example, gravitational waves might suggest a softer star, while NICE data suggest a stiffer one. Cooling rates might demand more protons than expected, while spin limits suggest fewer. Reconciling these results has proven nearly impossible. It's also possible that the standard model of physics is not enough. When neutron stars get really dense, we might be seeing the edges of what we know about how matter works. As long as new forces, particles, or even deeper structures like preons are unknown, there will be no way to come to an agreement. Physicists are trying to use ideas that have been tried on Earth to situations that Earth will never be able to recreate. Heavy ion collisions at particle accelerators like the Large Hadron Collider can mimic certain conditions inside neutron stars. They produce quark-gluon plasmas and let scientists study symmetry energy. But the densities and timescales involved are still far below what neutron stars reach. This means results from accelerators can only go so far, and sometimes they contradict what astronomers see in the sky. On top of that, neutron stars themselves may not all be the same. Some could have pure neutron matter cores, others could host quark soup, still others might be strange stars or preon stars in disguise. If that's true, then the lack of consensus isn't a flaw in science, but a reflection of reality. Neutron stars may come in many flavors, each obeying its own rules. This idea of diversity could explain why no single theory has ever matched every observation. The debate also rages because small details matter enormously. For instance, the proton fraction inside a star might be 10% or 15%. That tiny difference changes whether the star cools slowly or quickly, whether it resists collapse or tips into a black hole. Measuring such small differences across cosmic distances is nearly impossible, so models remain locked in disagreement. And then there's the issue of timescales. Neutron stars evolve over millions of years, cooling, spinning down, and sometimes colliding. But our observations span only a few decades. We're watching a tiny slice of their lifetimes, trying to guess the rest. It's like glancing at one frame of a movie and trying to reconstruct the entire plot. Naturally, scientists end up with different interpretations. People also don't agree because there is a lot of information on both sides of many arguments. For instance, quark matter could explain some mass and radius values, but it doesn't fit with data on cooling. In theory, hyperons make sense, but they soften the star too much, which goes against what we know about heavy mass neutron stars. There may be exotic condensates, but no one has found clear evidence of them. It seems like each idea fits some facts, but not others. Neutron stars are like locked vaults of the universe, holding secrets so deep that even our best science can't yet crack them. Each new observation, each new theory, only deepens the mystery of what lies within their cores. Are they quark soups, exotic particle condensates, or something beyond all human imagination? Until we find out, neutron stars will continue to be cosmic riddles that remind us how much of the universe remains unknown. If you enjoyed diving into this mystery with us, don't forget to like this video, subscribe to Beyond Horizons, and let us know in the comments what you think is really hiding inside a neutron star's heart.